inside the switches, there's so if you're doing things like SACN, which is like mining,
Oh yeah, yeah.
so we support all those like VLD Asha,
Cool.
which is all mining. So we support a lot of there's we have if that's the kind of lighting we're talking about in like Martin.
Yeah.
So Harman's a big partner of ours, and Harman's their lighting brand.
Awesome. No, that makes sense. Yeah, it does. They need you.
And so
Wow.
what's the other one I'm trying to remember? They're switching. They're out of Milwaukee, not Milwaukee, but close to Madison, Wisconsin, and right now they use like a Cisco switch to an end of life.
Okay.
And Hello. Hi, everybody. Welcome. Thank you so much for coming. We're going to get going here in just about 90 seconds. We'll be live on our stream, so if you guys could just find your seats. If there's not enough seating, there's a you can set up over on that side of the room. But yeah, we're going to get going, so thanks so much. And we'll get going in about, a minute or two. Nice. It works. We're live now? Yeah, this is the first break, I think. Do you guys need this? Let's do it. Oh yeah, sorry, I forgot about the thing. Great. All right. Hi, everybody. Thanks so much for coming. We're going to get going here, and we've got a full day of some really amazing talks and demonstrations, and there will be plenty of free time in between to interact. So my name is Connor McGill. I'm the director for PIXERA USA. I work here out of this office and work with my colleagues Tavia Mora, our principal creative technologist, Ryan Jones, our media systems engineer, and Abby DeLeve, our technical solutions specialist, who are all out of the office here. We're being joined by Harry Gladau, our executive director from Germany, and Philip Reitinger, also from our hardware team in Germany. So we're all, and Bateman, of course, Bateman, our trainer, is here as well. So that's the AV Stumpfel team here today. We've got a wonderful lineup of speakers. They will all introduce themselves in time, but as I mentioned, we'll have plenty of time to interact in between. We're doing 2 speakers at a time and then a break. We will be streaming live all day, so we're going to try to keep it pretty on the money when it comes to timing. We'll do our best. And yeah, so the first 30 minutes, I'm going to kind of explain some of the ideas that brought this event together and what we're trying to accomplish today. And then we're going to jump right into a demonstration. The Exquisite Sandwich, which is a live ST2110 powered interactive real-time system that have been engineered by our friends at SmileSoft, and then we have some speakers throughout the day. First of all, massive thank you to Tavia and Ryan and Abby and everybody on the PIXERA team for the amount of work that went into this event, and really it was no small undertaking, and we some really exciting ground here that we're going to share with you. Also, a massive thank you. Oh, sorry, can I get my slides up there on the? There we go. Massive thank you to our partners in the event: Panasonic and Panasonic Connect, Megapixel, Row Display, Netgear AV Matrox, and of course SmileSoft, our creative content partners. Couldn't have done that without them. They've all furnished gear and support for this event, and we're very glad to partner with them. So, before we get into any specifics, I'm going to just take 30 minutes to kind of talk a little bit about this transition from legacy AV transmission and processing into an IP or software-defined environment. This is kind of some of the information that I wish would have been aggregated and presented to me, or it would have been helpful for me when I started getting exposed to these concepts many years ago, and I hope it's somewhat helpful to you and at least gives you a sense of how we're thinking about these things at PIXERA. So there's kind of a growing crescendo of background music about these IP concepts entering into different workflows. There's been some pretty significant mega projects that are on live that are based on ST2110 and some of the next big generation of mega projects seem to be using that technology at the core. It's been proven in the broadcast industry now for 5 or 6 years. There's still a little bit of ambiguity around this, at least in my discussions. I find that some people are harboring certain misconceptions. I've certainly harbored misconceptions, and I still am concepts as well. But the goal of this presentation is to kind of shed light on some of the ambiguity. And then the last part of the premise is that people here in the room are really the ones who have agency to kind of oversee this. There's not going to be any dictator who comes down from on high who says you have to do this. You have to choose to adopt it because it's better for your workflows. So we're talking about the background of our company quickly, a little bit about the history of video over IP standards, why IP is better, is with some specific examples, and then our approach at PIXERA. So many in the room know our story, so I'll really quickly breeze through. AV Stumpfel is celebrating its 50th year this year, which we're really excited about. It started in 1975 with Reinhold Stumpfel tinkering around with Leica slide projectors in his attic, and that evolved to a company with over 100 people, 4 offices globally, a whole lineup of products, including our projection screens as well as our media servers, all centered around the idea of improving the quality of the presentation of visual images in live events. We are a real-time media processing platform for big pixel spaces. Not that we can't handle a single HD screen, we absolutely can, but really PIXERA comes into its own when you're talking about big LEDs, lots of projectors, really large distributed rendering systems. We take a user-centered approach to the development of our products. We don't add anything to the product that will make it more confusing or more, harder to use. We build our own hardware to run our software, and that makes it run really well in environments. And we are a community of really enthusiastic users and professionals who support projects in a very active way. We don't just release a new version every 6 months and say good luck. We try to get involved with R&D and validation and system support and those kinds of things. Our product started, really in the car shows of Germany, where we were being asked to do uncompressed 8K, 60 frame a second, 444, uncompressed image sequence playback, and that has really been at the core of PIXERA ever since. Is that high fidelity, stable, reliable presentation of imagery and audio in these environments. Our product has 3 pillars: the render engine, the user interface, and then the APIs that allow you to customize that experience for any kind of use case. We've done big projects, worked with Metallica and Adele and Valorant World Championships, Chris Stapleton, lots of big airport projects, virtual production studios, cool lobbies, and projection mapping. So that's the background on AV Stumpfel and PIXERA. If you have any other questions, you're welcome to find any on their shirt during the breaks or lunch. So the title of the presentation, Pure Pixel Data and Software-Defined Workflows, to quickly define that, pure pixel data it's kind of this idealized concept where the data that you're working with, and this applies to audio data as well and non-audio video data, but really we use I use video as the primary concept here because it's more tangible, it's a little bit more visual. But pure pixel data is the idea that you can take kind of unconstrained RGB data at a high bit depth and maintain that level of fidelity and flexibility throughout the signal chain, so that when you capture that or create that content in a piece of software or with a really high-end camera, and you then need to ultimately represent it on a screen or a projector, you want to maintain that kind of unconstrained creative and technical environment. But traditionally, we've had to constrain it because we've had to put it through analog pipes and put it through digitized analog pipes. But we're now emerging into a new environment where we can kind of break free from a lot of those constraints. And software-defined workflows is just the idea that any kind of intervention or transformation to that data can be done at a software level and doesn't require some specialized FPGA-based or hardware card-based solution, which again is a function of these IP systems. So the thesis is, again, just to really restate it, is that this is better. It actually provides benefits. When you break away from transmitting video over SDI or HDMI and transmitting audio via XLR or and bringing that into a more packetized environment, that you have more flexibility, more scalability, more possibility for automation, and it's less expensive to scale those systems over time. They're inherently more future-proof. So kind of backing out, what is really the mission? I mean, before we get into any specifics, well, it's to capture or create content using the highest quality available tools, to transmit it, then to reproduce it to the human perceptual system, either a visual system or auditory system, in a way that achieves the desired effect. And we have all these insanely sophisticated camera sensors that are cinema camera or broadcast cameras that these companies like Panasonic put tons and tons of R&D into being able to produce raw 16-bit video frame data, and being able to work with as close to that throughout the signal chain is really would be hugely beneficial. You've also got these virtual tools like Cinema 4D and Unreal that create these photorealistic environments as well. Then the processing, of course, we want to be able to provide these real-time flexible workflows so that people can work with the data as they and see the results of their actions immediately on the screen or in the immersive room or wherever it might be. And then we have all these really sophisticated display technologies like super high-end row tiles or Panasonic projectors that use 3-chip DLP, super high-end LCD and OLED TVs. So again, we don't want the piping, the transmission, to be the bottleneck. And at least when I started engaging with these concepts, I was overly focused on the transition of the substrate from HDMI and SDI over to copper and to fiber than I was the nature of the data itself. So when you look at an SDI signal, for example, it is a synchronous digital transmission of basically a waveform. And that is limited in a lot of ways because you still need to use things like sync pulses and blanking intervals to be able to interpret that data correctly. So even though it's a digitized signal of ones and zeros, it's being transmitted more like an analog waveform on the left. The same is true about HDMI, although it uses a slightly more sophisticated methodology that has some kind of duplexing or bidirectional communication capabilities. And DisplayPort is really a packetized solution, but it's still constrained in that it's not open, it's proprietary. And this is, of course, as time marches on, these frames just keep coming, and all of this data is encoded as a frame, right? So not as a line, but as a frame, which means it's much more difficult to decouple certain parts of the visual data. Not to mention the audio and video are coupled together as well, which is further constraining. So traditionally, using this kind of video signal or data signal transmission required like really sophisticated FPGAs and application-specific chips, and that was just because they were the only thing that could provide the level of parallel processing that you needed to be able to handle really high fidelity video and audio. They could produce consistent low latency results, and you could parallelize processing across multiple cards. Now, the downside is that it's a much longer development cycle. So, if you want to switch to 4K cameras in your environment, well, now you need a whole new, core system to be able to handle that new amount of traffic. It doesn't scale freely. It's also, the kind of operations that you can perform on that data, are constrained to what was kind of built into that chip. That's not totally, accurate. You can do quite a lot with FPGAs and updating firmware, but as compared to something that's fully software-defined, there's no comparison. Another advantage of these kind of serial transmission methods was that a workflow kind of emerged from the design. So if you had a camera here, and you had a switcher here, and you had a display here, and you plug one into the next, an image would appear. You could kind of understand what that workflow was going to look like just by how the system was laid out. That goes away with the network. As you can see from our system diagram over here about the exquisite sandwich, somebody has to kind of explain it to you because it's not immediately obvious where that data is flowing from and to. But again, there's flexibility in that because you can multicast or you can decouple audio and video or decouple certain parts of the stream. So some of the limitations. And again, just to reiterate, there's a certain tendency, at least that I've found, for people to kind of overlook the importance of this transmission of the actual method of transmission, not just the substrate upon which it's flowing. So moving over to network switches and SFP connectors and copper connectors and using things like multicast, like that's the important kind of facade of all of this. But at the heart, when we move to a packetized workflow, we have advantages. And that's been borne out, and my cat memes are going to absolutely pale in comparison to Michael Kohler, who's going to speak later, but they are inspired by him. So, these benefits are kind of self-evident when you start to learn about it, and we've already taken advantage of IP for other types of video transmission. So, early internet, we had to get cat memes, those videos, those viral over, E-bombs world, and those were all using early video over IP, but those were never really meant for the Pro AV space, for doing huge live shows or for doing immersive experiences. Even today, if somebody delivers content in H.264, H.265, that's not good. That's not what we want. That's not made for us. It's made for a different purpose. So then there were some attempts to bring video over IP. I think when I started my journey in this industry over 10 years ago for a small integrator in Minneapolis, I think the first week my boss was like, here's a laptop, go take AMX University, that's how you'll learn about this industry. And I remember doing a module about their JPEG 2000 encoder, and they were talking about the AV over AV-IT convergence, and it was like imminent, and again, that was 10 years ago. So, there's been a lot of attempts at this, SDVOE, there's, Crestron's NVX, AVB, but none of them have been high performance enough or commercially viable. That's kind of my assertion. And by high performance, I mean extremely high data rate, so really high bandwidth, really low latency, microseconds, milliseconds, and synchronization across n number of sources and display nodes, as well as zero tolerance for fault. I mean, literally zero. I mean, blipping to black in the middle of a concert with 80,000 people at it, or the keynote for Fortune 50 companies, that's just not acceptable. Whereas if you get a little lag in your cat video, that is acceptable. And we needed this family of standards to be ambitious enough to solve for all these problems, to be reasonable in terms of infrastructure costs. Now this is still, but it's coming. And open standards with low or no licensing costs. I think those were the important features. So to solve all these problems, there's not just, I need to speak into that, sorry. So to solve these problems, it wasn't just one standard. It's actually a family of standards. And the family of standards that we're going to discuss today, and different people are going to talk about different parts of this throughout the day. IPMX, which is kind of an initiative by AIMS, the AV Alliance, to make this a little bit more accessible, a little bit more quote-unquote plug-and-play. NMOS is the kind of control layer. PTP is the timing method, which you're going to get a graduate degree in from Michael Kohler later. And then SMPTE 2110 gets a lot of the love because it really solves not the most difficult problem, but kind of the most obvious problem, which is how do we get uncompressed or this really high amount of data over a network in a way that is reliable and low latency. So SMPTE 2110 itself is based on a whole family of standards that basically goes, if you drill down far enough, it gets you back to the foundation for packetized network traffic, which is FC 3550 standard from, I think, the internet.org. I don't know, the Internet Association. But you have previous attempts by SMPTE itself in the 2022 standard to define a lot of this that have been kind of revamped and added into 2110. And the big innovation that everybody talks about with 2110 is that they've split the audio, the video, and the data into separate what are called essence streams, so that each stream has its own RTP header that says, okay, I'm an audio stream at this bit rate, and this is my format. I'm a video stream. This is my RTP timestamp. I have this color bit depth. I have this frame rate. And you can then take those streams, decode them, transform them independently of one another, route them independently of one another. What is ST2110 in practice? It's actually just a bunch of PDFs online that's published by SMPTE. They're $50 each. You can buy them. There's, I think, 7 or 9 or something. Some of them seem to be like totally boilerplate, but the big ones are -10, which is the timing definition, which is based on PTP. The 20, which is the uncompressed video. There's 30, which is audio, which is based on AES 67. And there's 21, which is the network shaping, which Alex Pendleton is going to talk a little bit about later. And then there's the -40 for sending non-audio or non-video data. And those are the big ones. You can read them. They're quite human readable. You don't have to be a software developer or a hardware engineer to understand these. I mean, there's some pretty mathy charts at certain points, but if you took a little bit of high school or algebra, calculus, some synapses that have been dormant for a long time will start to light up again. So this is kind of a depiction from Wes Simpson, who's a big name in the SMPTE world, of how these different essence streams get packetized and sent over the network. And so going back to this idea of FPGAs and application-specific interface chips being or integrated circuits being the only way to do this, because they're the only thing that could provide the level of latency, reliability, and parallelization. Well, we've taken advantage of the forward progress of video games and AI to ensure that there's a big supply of GPUs being able to process these packets using parallel processing on a GPU as opposed to an FPGA. And the high bandwidth is now solved by the switches on the network by companies like Netgear. You have sync being taken care of by PTP instead of Blackburst or tri-level Genlock or frame sync. And you have the low latency and zero fault tolerance being taken care of by 2110. And then the next layers of interoperability and ease of use come from NMOS and the control layer, and IPMX being the kind of quote-unquote plug-and-play, which IPMX, we'll talk about in a second, is still very much in progress in a lot of meaningful ways. So again, PTP, Michael Kohler has a big live demonstration of this, so I won't go into too much detail, but it essentially allows you to ensure a super high degree of precision and accuracy in your system. And the two kind of the two thresholds that I flagged when I was starting to research this were what is the lagging interval between audio and video signal when you notice? And it actually happens to be, like, at the smallest interval, about 20 milliseconds. On the video side, 2 quadrosync cards can keep a video noticeably in sync on an LED wall at 60.0012 hertz, which calculates to 1.2 milliseconds. PTP can synchronize the system within 1 microsecond, worst case scenario, if it's functioning properly, which is several orders of magnitude more precise. So it's PTP is used for things like high frequency trading and for, like chemistry, organic chemistry research to do isotope decay calculations. So it's for us in our video and audio systems, it's definitely, it's got the juice. NMOS. NMOS is a control layer. ST2110 doesn't define control at all. There's nothing in that standard that handles routing or scheduling of streams being sent anywhere or even announcing themselves. So NMOS, the two big elements of NMOS that come up are ISO4. ISO4 just is, hey, I'm a source. Here's my session display or a session description protocol file, which is basically just a header file. It just says, I have this resolution, I have this frame rate, I have this bit depth, and it's just announcing itself to the network. And then ISO 5 is the routing capability. So the two big things it has are the ability to either do it instantaneously or on a schedule, and do it one-to-one or one-to-many. So very simple concepts, something that seems essentially, almost childish in its simplicity, but when we're starting to build these standards out, that this is the level of functionality that's just getting built into some products. It's just being able to say, hey, I want to send this source here and here on a delay. And IPMX is a way to kind of integrate all of these standards into an easy to use and easy to operate kind of consumer-ready package. And that includes things like relaxing the timing standard. ST2110 requires PTP. PTP is fairly difficult to set up if you don't know what you're doing. It's not something you'd want to assign to a field tech who maybe has been on the job for 6 months and doesn't have a background in hardware engineering, which is something you frequently have to do when you're engineering systems that are field ready. You also don't have HTTP compliance or kind of that automatic recognition of a source or a display endpoint that something like EDID would take care of for you. IPMX is in progress. If somebody says, oh, our device is IPMX compliant, well, I just talked to them at ISE, and they're meeting at NAB in a couple of weeks to actually decide what their list of criteria is going to be for somebody to say you're IPMX compliant. So it's very much in progress. The big things are compression, because right now uncompressed data is really not acceptable on many, many networks because it's way too much. So figuring out a way to compress that down to 4-to-1 or even 8-to-1 or 10-to-1 without doing a lot of signal destruction is going to be critical. And then eventually adding things like USB, so you can automatically build in KVM functionality with this single connection is coming. How will it manifest? Well, basically through people like you in this room learning about it and deciding that you want to use it and trying projects with IP-enabled products like we have here from our partners, and the continued efforts of companies like us to improve the workflows, and we'll rely on, of course, the off-the-shelf switches and GPUs continuing to add functionality. Companies like NVIDIA, we rely on them heavily, and they it's going to require them to also innovate in the direction of our needs. I see it as kind of a 3-stage adoption rocket. There's the first stage is spicy NDI, I kind of call it. Spicy NDI being just the ability to send video or audio internally within a network and use it as more of a utility. What we're doing here, well, actually we are truly end-to-end here, which I'm proud of. But the primary function of ST2110, I think in a lot of systems today, is that it's breaking down the barriers between different systems at the core. But ultimately, a lot of the sources, so the points of origin, the cameras or the softwares, and the endpoints, the displays and the projectors, they need to add native functionality. So the middle out is kind of the growth for all my Silicon Valley fans, and then the final stage, which is long-term, multiple years, 5-10 years, is where if this is successful, you start to see it become the middle of the bell curve of our projects. The average project is an ST2110 project. Okay, so I have about 7 minutes to get through some ideas behind why IP is better. Software-defined workflows, virtualization is one that gets brought up all the time. I like to think of, the Las Vegas Convention Center, for an example. The amount of racks that get rolled in and out of that convention hall every single week with the same GPUs and audio processing units in them that could easily be virtualized to not the cloud, not an AWS instance, but some server farm that lives in that building that you could just have a fiber drop to. Now, of course, there's a lot of entrenched commercial relationships that would stand in the way of something like that. But technically, we're approaching feasibility for something like that, where you wouldn't need to have any gear on the floor. It would all route back to a server farm that you could then just basically rent space on for the weekend. And there's many examples. Hitless survivability is an example of the 2022 -7, or the redundancy element, which is in traditional AB networks or red-blue networks, basically you have to maintain your own heartbeat monitoring or your own manual oversight of these systems when they lose sources or certain parts of the network go down. But with 2110 switches, you can actually program that intelligence into the switch so that when a source goes down, the switch actually can identify that and send that back upstream, and then automatic switching activity can happen. And that can all happen in less than a frame, or less than a couple milliseconds. So that the guest or the viewer doesn't really know that anything happened. This is a software-defined workflow that actually some folks in this room worked on at the Valorant World Championships. This is an example of what's possible when everything's in software. So there's a virtual game being played by these players, Valorant, and the goal is to kind of create all of these interactive in-venue moments for the viewers. So what happened is, instead of using a control panel and programming a bunch of macros and calling it over the comm system and trying to observe all these players, the system was programmed to basically automatically detect game activity through the Barracks API system and then spit that out via OSC into PIXERA, which then triggered different Notch-LC encoded videos that played on top of the IMAG, so that the whole system was automated and the operators sat there with their hands behind their head or something. I don't know. Cody can tell you, he was on the project. Self-service is another cool example. That's Max MSP, which is a really cool example of a software-defined, or a piece of software that gave birth to so many cool creative workflows. It was actually Ableton was born inside of Max MSP, and Ableton grew to actually consume Max MSP and now owns Cycle 67 or whatever. But the idea with this is, nowadays in a lot of different environments, if you need to add functionality, you need to go out and buy a new product, or you need to ship new gear on site. But in a truly software-defined environment, if you need functionality, you can just go online and buy a plugin. And we have an example of like a SDI scope, which in 2110 world, you open Wireshark and you can then get this plugin for Wireshark, which essentially just turns your computer into an SDI scope or a video scope via software. So it's a piece of software. Yep. And this is the really exciting one I like, which is last mile compositing. So that's the exquisite sandwich is really meant to illustrate this, which is, in the past, if you had a simulated workflow where you have a rock concert with a performer who's walking across the stage and you have a camera following them, and that camera's feeding into a notch block, which is creating interactive particle system that follows that person, we would say, okay, well, basically, you would need like 4 really expensive real-time servers that are all synchronized perfectly. You would then need a bunch of 4K LED processors, and you would need to think in terms of UHD rasters. But in this new environment, the camera can feed its signal directly into a compositing server. You can then take a proxy of that, feed it into a real-time server, just one real-time server, which are the expensive ones, and then you can basically pipe the composited result of those two things into a compositing server and into some of these new 8K processors by megapixel. You could then not only decrease the number of servers in the system, but the average cost per server pretty dramatically. So we're already costing out some systems for live event where it's about half the amount of servers it used to be. And finally, ANC, ancillary data. Traditionally, you were limited to whatever was available in the horizontal or vertical, the HENC or VENC space of the SDI signal. But now, this is actually going to be part of IPMX. You'll be able to send data that's completely unconstrained in terms of the bandwidth or the format. So you could send UV coordinates or mesh data along with that texture data to reassemble 3D objects upstream, or send the result of some edge computed calculation from your tracking camera or some other appliance that you buy. And of course, I've already mentioned this, but all of those FPGA-based and application-specific integrated circuits can converge on a very limited set of consumer-available electronics, including GPUs, DPUs, which also may eventually merge into one. Again, back to NVIDIA if they decide that that's a commercially viable solution, and then switches and transmission cables. So at the end of the day, we really see this as network engineering and user experience. You know, what's the control interface that you prefer? So again, we come back to the pillars of our software being the render engine, making sure that all the data gets where it needs to go, when it needs to be there. The user experience or the user interface, providing a kind of a front door into this experience for the broadest scope of users as possible, and making sure that our APIs are still accessible for all aspects of the software. So day one, we've implemented the NVIDIA Mellanox RiverMax card. You have access to the full 100 gigs of that card as an input or output. We don't constrain you in terms of the number of streams, the resolution of the streams, you know, we've begun providing these servers for certain beta or experimental users to explore these workflows. We still have quite a lot of work to do, but we've recently added the ability to write your own SDP files in the software. You can generate a stream right inside of mapping, just like it's any other stream, NDI or DisplayPort, and then you can now participate in NMOS as a client. So that is a little bit about the background of this event and PIXERA. Up next, we're going to take about 3 to 5 minutes just to transition, because SmileSoft are going to be doing a kind of interactive demo that we need to do a little bit of setup for. So give us 5 and we'll be back with SmileSoft. appreciate you taking your spot again.
Test, test.
Okay, we're just gonna keep the cheese knife.
It goes badly. Hey Connor, do I escape out of this and open up my thing? Bada bing. Also, I thought you did a great job. Perfect. Thank you. Ooh, for some reason, can we reset the cache? This is old. We had to update the website 'cause this is outdated. Oh, there we go.
No, it's just a cache.
There's a cache thing. All right, we're Gucci. Check. Yeah.
Close it or open up incognito. Scare everybody.
Perfect. Give me some love. I need some of your energy, thank you. All right. No, it's pointing to your heart. Oh, yeah. Are we ready? Are we ready? That's what I'm talking about. This is great. All right, everyone. We're SmileSoft, but before we start, I want to do, to break the ice, a quick joke. I can only stand in this area. I want to do the whole Tim Roth walking around yapping, but we can't do that today. So you'll see me do this little bouncing. Here we go. Why did the audio stream break up with the... Why did the video stream break up with the audio stream? Because they weren't in sync. All right, one more. Okay. Let me just make sure it's a good one. Why do broadcasters love SMPTE 2110? Thank you. Because it lets them ghost SDI without any hard feelings. All right. There, that's what I like to see. All right. Ice broken. All right. So we're SmileSoft. I'm Smile Walker. Hello. My mother named me Walker. The internet named me Smile. This is Landon Looper. Nothing.
Hello. Oh, hello.
There we go. And we are here today because we made the sandwich that we're going to be looking at together. But also, we're a couple of artists and technologists and futurists who've been working with making things over IP for the past 15 years. And we're going to show you some of that before, the before action we were making a couple years ago, 10 years ago, the Brooklyn Mirage job that we did that used SMPTE in a big way. We're going to talk about the sandwich, and we're going to have some ideas and questions. One thing I want to bring up is that I was on the Uber on the way here, and we were having this conversation, talking back and forth, and it was really great because it was in real time, and it made it possible for ideas to happen. Here, we're not set up for this. I'm looking at you, you're staring at me, it's terrifying. We have a time for questions. If you have a question at any point, please, because you got to try to hold it in your head the whole time. That ain't it.
Yeah,
so
help us out.
Help us out. We have an hour. We got about 26 minutes of conversation. So please, we're hoping for the rest of that coming through y'all. Okay, let's jump into it. Hello, we're SmileSoft. Oh yeah, we're gonna be reading off the website. Now, we are a research and development company specializing in innovative software creation, world-class experience direction, and holistic system design for interactive experiences. The big thing here is holistic system. Okay. holistic systems for interactive experiences. We have, okay, there, this is the big part. Founded in 2020, we're dedicated to creating, thank you, I saw you, be prepared for that, creating engaging new media experiences that utilize emerging technologies not only to entertain, but empower the audience. As futurists, we are laying the foundation for tomorrow's media and today's, where the audience can interact, inspire, and be a part of the stories that they engage with and help shape. We are here. The present and the future is giving the audience agency. As you know, with your aunt and your boyfriend, they don't want to go to the movie theaters anymore. They can watch it at home on Netflix. They want mediums that can talk to them and respond to them, like we see in sports and streaming and gaming.
Kiss cam.
And the kiss, see, exactly. The kiss cam could be you. We don't have a kiss cam here today.
That's why they broke up.
Nice. Okay.
They didn't, or they.
We believe that the future of media lies in real-time interaction, a space where the audience is no longer passive consumers, but active participants in shaping their experiences. By utilizing the power of IP-based systems, we can create environments where people can come together, collaborate, and contribute in ways they feel immediate and meaningful. And, you know, the car ride here in the Uber, the conversation that we were able to have was so exciting because I didn't know this guy. And similar to where we're from in New York, the best part isn't being in your bubble with people who agree with you. It's about being in a bubble with people who don't know you, and you can have free perspective talking back and forth. And that's what we're now able to do with these new mediums over IP. Now, we are going to say...
People that weren't supposed to meet, they weren't going to meet.
They weren't, exactly. Talking. Everybody here, exactly. And what we do at SmileSoft is we're a bit of a bridge between yesterday's media and tomorrow. And also we have, we have the ability to work with clients that have dreams and aspirations for things they've seen and want to do and are able to express them in a way where we, an R&D company, can take that in and figure out ways to make it possible. Where others might be afraid of being in that foundational territory, for us, that's the exciting place to be. Making the foundation for these mediums is one of our huge passions. And it's been great working with these teams, PIXERA, and everybody, because similarly, this is the difficult problems are what we're attracted to, not afraid of. And if somebody has to make this foundations, we're very excited and happy to be a part of doing it. Okay, how are we doing so far? All right, I like this. That's a good smile. That's a thumbs up. Okay, this is awesome. I'll keep the jokes till later. We don't need them right now.
Was that part of the bit, or do we have to clear the?
I don't know. We're gonna find out right now. Uh-oh, we're live.
Clear the cache again?
Yeah, probably.
This is part of our bit.
Yeah, this is live interactive theater. Are we out of internet? Zoink, Scoob. Yeah, can you reset the cache right quick?
Yeah.
I'm gonna do some crowd work. All right, so who here has been to the movies recently? Someone said whoop. Yeah, we can join the Wi-Fi.
Well, but it. Okay. Connor's gonna help us out.
Yeah, we're going over IP. Yeah. Is there any questions so far? You know, I know we've talked about a lot of deep stuff so far. Is there any? Okay, I didn't think so. Let's go.
Can you talk about how you see, like, a word that I always have heard when we talk about kind of futurism and how we use IP-based technologies to interact with audiences. Can you talk about how you see film presence and, like, you know, the idea of kind of that audience, you know, the performer and the audience and where that interaction, like, what excites you about that interaction and why that, like, how 2110 can kind of lead us to further in that?
Yeah. Not all. Some people get stage fright, and some people get the opposite. They get ramped up from the audience and their excitement. I think now the agency, also Loop's you in on this, the agency that the audience has to be a part of the show, whether it's something small or something big, it's, oh, there we go. Oh, okay.
We're connecting to Connor's hotspot on his phone. What do you have though? Do you have Verizon?
We
What?
well, we can just jump into the Samish, right? Because that stream is working. All right, can you ask that question one more time? That we're fully paying attention. All right, one more time.
Yeah, so you know, I always when we're talking about kind of audience and performer in digital spaces where, especially distance is concerned, we can get even greater distances. You know, talking about your Portals project, telepresence, or this idea that kind of you know the audience and the performer can engage over those distances is something that really excites me. Can you talk about how 2110 might lead to a higher level of engagement, or what about 2110 can bring more telepresence between performer and audience?
Oh yeah, what if you were watching a sport event and you could change the camera? You could switch your seat at home. These are. You went on this? Yeah. We're good over here. Coming back around.
Are we gonna finish the question?
Yeah, I keep getting halfway through and thinking about this.
Yeah.
Let's think about.
Sorry, I keep on hovering around you.
That's cool. So what are the new?
This is also part of the act, everyone. These are. I don't know. I would imagine something for something else.
Yeah, exactly.
They're plugging into the rack. This is the crash cart.
Yeah, exactly. Well, we're going to show you something that we made 10 years ago.
Oh, okay.
Hopefully, that can make this all seem like maybe it was on purpose. Okay, can we answer his Sim2 question now? Sorry, my brain's spreaded.
I mean, he was asking about projects like Portal. So the first page here is a behind-the-scenes photo of the Portals project, which is connecting two public spaces, one in New York City and one in. Oh, okay, yeah. It's connecting two public spaces, one in New York City, one in Dublin, Ireland. And now I think it's still in Philadelphia.
Yep.
And it's connecting to Poland, Lithuania. But this is when it was back in the fabricator shop that we have our studio in. But technologies like SMPTE 2110 are going to enable things like this, taking advantage of dark fiber and connecting venues and public spaces together is going to be a more common thing, including like holographic light field displays and things of that sort. And you would need the kind of data throughput that SMPTE 2110 has to push that kind of holographic or light field video feed, because you're talking about what's equivalent to like thousands of cameras and thousands of displays worth of pixels. This is Ryan, everyone, the systems the system engineer.
Yeah, we need some clapping right there. That's big.
And Philip was assisting as well. He flew in from Austria, or there he is. He's over there. No, so yes, yeah, it was using redundant mobile networks, and it's meant to go anywhere. Like in the future, things like national parks and places that don't have hardline internet. But it was difficult enough to try to arrange a hardline internet in Flatiron. Our best bet was like trying to piggyback off of like this coffee shop nearby, and the whole, the city was involved, and like the Flatiron business district, and but as you know, bureaucracy is kind of difficult to get an internet connection or to, even power, any type of infrastructure. But it's more of like it's a simple concept that hasn't taken advantage of the technology yet, but it's amazing how fascinated people are with it, of like 24/7, always on, public space, life size.
The window.
Yeah.
Someplace else, yeah.
Yeah. Though artists have been doing this since I believe the 70s. It was Kit Galloway. Did this with just analog TV broadcast technology.
Check.
And, it's still something that we have yet to fully explore.
I think the most exciting thing that, to answer your question, is now with SMPTE and being able to do real time, is making things that don't have a finalized ending. Seems like an intense thing, but what our job is we make things that are 80% complete. That's our job. We got to make things 80% complete, and then when we bring it in front of the audience lets us know what the last 20% is. It's always a collaboration with the audience, and they let us know how to finish the project. So we as creatives, it's also exciting for us. We're not illustrators. I'm not exactly sure where we're going or what it's going to look like at the end, but I do know where we're going, and working with the audience and their input in real time is really important for our projects to be able to adapt to the audience.
But Portal famously, or portals.org, famously was shut down due to some incidents of people using it in ways that were considered inappropriate, which to us, so we didn't have creative control of this particular project, and that's fine. The people who created it are excellent folks from Lithuania, but it was interesting because they didn't see it as the audience finishing it. It was the audience like misusing it, and then it was no longer a 24/7 live stream. And our experience in past projects with live streaming is that if you let people do the inappropriate things and then you don't give them the attention they're looking for, they get bored of it or the novelty wears off. It's, anytime there's new technology, there's going to be bad actors that show up, and if you let them, you let the trolls troll, and they eventually move on to the next frontier.
Post-roll. All right, so we're going to play a couple projects specifically for 10 years ago. We're not going to go 20 years ago. We're not going to talk about our first day playing Roller Coaster Tycoon. We're going to go just 10 years ago from this year and show some examples of our attempts at real time and connecting audiences and what we're talking about here. This first one is something that we did back in 2015. It's called Living Room Today. Simple idea. It's a simulcast show that connected at least three different countries, and gave the audience the time and participation of being live at the show from anywhere. We did 15 shows, over 100 performers, and we always connected a visual artist and a musician that did not know each other and combined them to make something that neither of them could have planned. They're always from different countries, and then we played it in real venues around the world simultaneously and also online. So anybody from anywhere, no matter how where you're located, you could come to this show. And also, there was live stream feeds of all the different people at the show. And like Loops was just saying, it was purely democratic. Everyone was allowed on the camera. And it wasn't just you have to be good looking or famous or popular. Everyone got a chance to be on camera. And it was amazing for us to see, once people realized that they were being watched and a part of the show, not just watching the show, they went from the nerd neck to, everything changed. They put a little hat on. They did a little jig. It got exciting. And you could see that based on how long they stayed a part of the project, stayed watching, that the interaction was really important for them. And like Loop was saying, unlike the portals, when some things happened, they had to turn it off. We were looking for what people were going to do wrong, and instead of just canceling them or blocking them, we knew that our audience was so mixed with people from all around the world, they didn't fall for the bait of the trolls. And it was beautiful to see people trying to ruin our show, trying to take all the attention away, and accidentally becoming a great bit inadvertently. Then after they got their attention or didn't get their attention, they would always ask, "What's the show? This is pretty cool."
One thing about that we've talked about a few times is how this was years before the pandemic, and so now it's like this is a pretty well understood concept now, but it was surprising how many people didn't get this, or they're like, why would I watch a show online, or why would there be any reason to, or anything, and now it's something that's just part of our.
We're gonna play two clips. We're gonna go here on the screen and play just a couple clips that these are all user-made clips. We didn't make any of these. These are all made by people that were attending the show and just wanted to participate in the show, which is fantastic.
I've been wanting to click the play button.
Want to hit it?
Yeah.
No, just get close. All right, here we go. Let's go full screen. So here's one. This is the first living room show in 2015. As you can see, there's people on the wall that were streamed from all over the world. There was musicians playing live at each location. Some location in Los Angeles wasn't playing. Somebody in Hungary was playing. When somebody in Hungary was finished, somebody in Minnesota was playing. Everyone watching everyone. There would be laptops on every set that we built that looked like a house living room. And there, the audience could interact with the people from other locations. Here's a house party that was also connected to that. That was part of the stream in the beginning, one of the many feeds. And all of a sudden, people realized at the show, hey, we're going to that feed right there. And every show would start in location A and in location B. And we'd always mix a whole bunch of different types of music. Oh boy, here we go. See how that looks? Yeah. So this is what we remember in COVID. This is what shows started to look like. And we weren't using them because we had to do it. We made this so anyone could get there and be a part of the show. And so when COVID happened, when shows became like this, we were hired a lot to help Boiler Room and different clients work in this new medium. Let's do one more, just because this is a great example of interactive theater where the audience. Can you guys hear it, or can you all hear it? Okay, cool. So this is Pensée de Création. This is back. Make it big. Let's go big screen. Oh my gosh. There we go. All right. That's what I'm talking about. So that was some 2015 absolute juice. And this is what I'm talking about, the 80-20 thing. Pensée de création are geniuses. We know that. But we did not know what they were going to do. I don't want to know what they're going to do. We want to create the framework for them to live inside of, and then we let them dance. Therefore, our job is to experience it live with the audience, and our reaction is just like the audience's. We're right there with them. And then we set our clients up, or the people that we're right with, even back here in the living room days, our job is to set up a foundation for them to dance. And then the floor is perfect, and they have their shoes. We just let them do their thing and create the atmosphere for them to create. And with SIMTI and with these, well, this is before all that, but this is over internet. We were able to have someone perform from Spain right here in New York, or Los Angeles, I guess. Next up, after that project in 2015, moved to New York from LA, and we made 8Ball TV, a 24-hour live public access online platform. This was our first big project in New York after moving from LA, after Living Room. We were brought in to help produce this. This was the dream they wanted to make, and they brought us in to how are we going to make this possible. It was very exciting. It was all about giving the audience the channel. Now you have the ability to make a TV show, send it in, or work with our team to make a show for you, which is really exciting. And then we made a show for 8Ball TV called CompUSA Live. Yes. We had a laugh track set up, but, internet issues. So CompUSA Live is a avant-garde performance series that blends digital absurdity with real-time audience interaction. We're not going to read any more. Let's just watch what that means. Believe it or...
You guys like jokes?
Let's go big screen.
Here's one. Knock, knock.
Who's there?
A computer.
Hey, Greg, curtain, please.
Do it, Greg.
Look again at that icon. That's here. That's now. That's us. Everything you know, everyone you love, everyone you ever heard of or followed, every human being who's ever in any way relevant, cool, or important, living out their lives. The aggregate of our memes and selfies, thousands of confident users, gaming platforms, and cryptocurrencies, every troll and shitposter, every top-ranked Redditor and vlogger, every coder and hacker, every admin and site moderator, every Tinder match hopeful, every ad blocker and VPN user, Etsy thrifter,
There's the
food
live
blogger,
audience in the left corner.
fortuner, every 50-page user agreement, every drunk tweeter, every influencer, every emoji, every UX designer and Fortnite gamer in the history of our new tech reality logs in here, surfing the waves on a vast, interconnected global party we call the Internet. The Internet is a very crucial part in our cosmic tech reality. Think of all the content posted by those dirtbags and hot chicks, so that in glory and in triumph they could become the first to hit 1 million likes and make sponsored posts for gourmet dog food. Think of the endless Facebook events pages visited by the inhabitants of one social group, on the scarcely distinguishable carousel of temporary apartment galleries, how frequent their reblogs, how eager they are to follow one another, how fervent their passions for the new tech reality. Our posts are total connectivity, the reality that in a new tech paradigm we have the most privileged position in the universe is fully supported by the glory of our inventions. Our planet is no longer a lonely speck in the great enveloping cosmic darkness of dialogue. Online, in all this vastness and grandeur, there is no sign that life could get any better than it's getting now. The internet is the only world known so far to harness our wildest hopes and dreams. There is nowhere else, from now until the end of time, that could...
All right, you guys get the point. We gotta move on from that. That was CompUSA Live. That was all real-time edited with custom software. And as you see, the background and visuals were done by the guy in the top right corner. That guy in VR, he was making the visuals. We had multiple cameras, switcher, and everything you're seeing was made in real time. This was in 2015. The live audience was able to pick cameras. The live audience was able to pick the background. And throughout this show, CompCoin, our cryptocurrencies, worth was going up and down, making the merch section worth more, or cheaper or more expensive. So during the show, the audience could buy more, price would go down, and the audience was constantly letting us know how much merch to sell. So little example of stuff that we did in the past. There's one more. I'm not going to show it, though, because there's just, this is all the past. But this was a video game that we made inside Minecraft that is created for the audience to tell the story. We created the foundation, and what the players did, the lore that they created, was then written into the game. So if Looper plays the game, starts the game, does something fantastic, the game doesn't just say, the game that's written into the lore of the game, and the NPCs of the game can tell you about what Looper did. So this game is, we started it and the audience finishes it. Everything you see in here was made by the players. Right now there were 60 people playing. We played when I looked in this morning. So this is, we create the foundation. We come in and interact with it to help the audience, because there's no way to do this yet for the game to update in real time for what the audience does. So we do it as the creators of the game and the mods of the game. And also in the game, the audience, if they're interested in that, you can join a certain faction called the Tellers and learn to write code, the Denizen code, that is the code for Azeros. So you can become a writer of lore if that's what you're interested in the game.
User-generated lore.
That's what I'm talking about. User-generated lore. Okay, so now we're going to go to our last project, or the Mirage project, the Brooklyn Mirage. So in 2022, want to talk about this one?
Yeah.
Nice.
So in 2022, the Booker Mirage moved from a multi-projector system to an LED wall that's roughly 200 feet wide and has this this structure behind it. And there's train tracks behind there, which would constantly be behind the venue. It's out in Bushwick in this industrial area. And actually, our Austrian friend Billy was our contact there. Yeah, exactly. They created this concept with some friends of his.
The Brooklyn Mirage had a dream of making the largest immersive venue in the East Coast, and their step of doing that was buying the wall, getting the wall, and then hiring us to make it actually possible, to make it work. Here we're looking at the system that we had to build in a month before the venue opened, and here in our studio is a recreation of and the tests of everything that we made for the system. Can you talk about the system a bit? How we made that happen?
Yeah. So the the raster is almost 4K outputs, which you can see here on these preview monitors. And there's also 4K touchscreens for controlling everything in the venue, as well as a Panasonic Kairos control. And one of the interesting things about this project is that we didn't want to deploy a SMPTE 2110 system, but given the scale and the time frame and the supply chain issues at the time, it was the most viable option. And we had already been doing some testing with SMPTE 2110, and we collaborated with our friend Jonathan Thompson with Point Shader, and he had worked with us to set up some of these test systems. Had a Mellanox switch laying around, which was one of the things that was also unobtainium at the time. Again, on this time frame, and the client didn't want to rent equipment if possible, and they're still using this system today. This is a transition test going with the Kairos, but this gives you a sense of scale with the cherry picker here. Yep, yeah, with the tile mapping, and we had a rack of Riedel transceivers and adapters from 2110 SFPs to SDI, and though one of the most infamous things was that the only reliable way we could hook up a Mac OS computer was via this Thunderbolt Blackmagic 12G SDI box that we would plug into the Riedels, because I think they had just made the switch to Apple Silicon, and all the dongles were a nightmare that didn't work reliably. This was a show that we collaborated with Rufus DeSole on creating an alternate version. Think of like B-sides and remixes. It was like an after party set, like after their main concert.
The big thing with this is just that 95% of artists came with a 16:9 show, and they were freaked about this. How do we make our show work in this venue? So one of our big jobs was to take the elements from live shows and make them work for this venue. So on top of making the system for the venue, it was really working with the 150 artists and the 10 different festivals to be able to quickly and rapidly update the background, show them examples, and make things not just on the fly, but quickly. Because every artist had dreams, and they wanted their show to look great in this system, and luckily it was possible for us to do that when we had a show Tuesday through Sunday every day for 7 months. All right, here's one more point of the show. Oh yeah. Okay, I think now you guys get it. It's a. Oh yeah, this is all done in yep, real time. You know what this is?
Oh yeah, that was when Yoda showed up in the audience.
Yeah.
We kind of
You know, the fun part about this show, or doing this venue, was via real time, is all the visuals are done live. Everything you were seeing on the wall was done live, and that made it exciting to watch the show because it's based on the audience reaction. It's our job to know when the phones come out, we're doing our job right. And it's a great cue for us. But if the phones are down, we know we need to spice it up a bit with the visuals. Here we're doing a live camera feed. And again, the direction was here's the camera, make it exciting for us or else. And lucky for us, this is something that we like, the pressure that we like to make the show as exciting as it is with just one camera and a giant wall. And then we had the previs. I'll show that really quick and then we'll jump over to Samish. Mm-hmm. This was a big thing for every talent, is that they needed to see what their show was going to look like, and every timeline was very quick. So we made multiple different versions, of previs for clients and artists to see what their show would look like before they got there. Also be able to see it through VR if that made it easy for them, but this was the, oh yeah, look at that. Okay, cool.
Yeah, that was one of the common issues which happens at many venues, but especially the more immersive they are, such as the Brooklyn Mirage, Coachella, Sphere, is that when the artist is creating the show, the scale of things, the pacing of things on a small 2D screen laptop, it may seem perfectly fine, and then you see it at scale and it's moving way too fast, and it's too immersive, it's sickening, and then you have to scale that down. So having a proper previs and using virtual and augmented reality helps you tune that in before you get on site, and it could save you days in having to fly out early and set up the show, and so it's a valuable process.
And necessary process, for once again, this is new to everyone, and new means scary. Everyone likes the Lindy technique, so the previs was necessary for the trust and for the artists to really know what it's going to look like beforehand. And then after they saw the show live, it was essentially one-to-one, which is exciting that we were able to bring that to them. All right, let's do some Samish stuff. Believe it or not, we did some time. Oh gosh. Backwards. Okay, so I'm going to walk back into the Samish land, and then we're going to talk about what we did here.
Okay,
Break down the Samish for them.
I'm gonna walk you through it. So we have a backdrop that's rendering in Unreal Engine 5.5.3, and you can see there's clouds moving, the trees are swaying a bit, and then we have a fluid particle simulation running in Touch Designer, but just the simulation, and because SMPTE 2110 has uncompressed video feeds, we're using the RGB channels, actually RGBA as well in this case, because we're sending 32-bit per channel position data over 8-bit per channel video feeds, and we're doing some bit packing, which Touch Designer actually has some built-in packing and unpacking that we had to reverse engineer, and then the particles are being rendered by a custom renderer in Unity that we wrote for this type of effect, which is also pulling in the Unreal background, doing some refraction. One of the analogies that we use to describe this is that film and TV workflows, they're offline, pre-rendered, pre-simulated. You could have a fluid simulation, physics simulation in Houdini. You could then render that in Maya, Arnold, have some camera footage, and then you would composite that in, say, Nuke. And in this case, we're compositing it with PIXERA and simulating in Touch Designer instead of Houdini, rendering an open world in Unreal instead of RenderMan, what have you. So this is what SMPTE 2110 and PIXERA's implementation of it enables. And we haven't seen anyone really utilizing it like this yet, and maybe there's a few people doing it or prototyping with it, but it's something we'd really like to see more of. So that's just our first iteration of this, which came out of some of our testing and prototyping with our first SMPTE 2110 system at the Mirage. And yeah, feel free to play with it. There's a yellow rectangle that has the interaction piece, and I forgot to cover how the interaction is working. There's a Panasonic UE160 PTZ that has a fiber line out of it, and it's going directly from the PTZ over SMPTE 2110 to the to the PIXERA server that renders the particle simulation. And we're using some machine learning frameworks that didn't even exist a few years ago to get a fairly accurate point cloud depth map, similar to a Microsoft Connect or Orbeck, RealSense, what have you. And so it's an exciting use of this technology that we hope to see more of.
But you nailed that. Okay, do we have any questions? All right, Andy.
Yes, yeah. So Unity is rendering the fluid and doing some refraction, and so it's there's some custom rendering APIs in Unity that are quite powerful. So we had already written a fluid renderer for a few other jobs. So.
And then PIXERA to composite out to the screen, or is it what's doing the compositing of all these layers?
Yeah, so PIXERA is putting everything together with SMPTE 2110, and there's, like, in the case of Unreal, PIXERA has an integration for it, and then everything else we're using Spout, at least for now, but there'll be ways in the future to synchronize this all better, and especially for like multi-server sync, which is one of the big things for this. So we could split the fluid rendering across multiple nodes, the open world rendering across multiple nodes. But it's a situation where PIXERA is doing compositing, but it's also routing this particle data, which then gets rendered. Is that
it makes sense. So the image on the screen is ultimately Unity is rendering its particles on top of the Unreal background, or are those coming in as two separate streams and getting composited downstream of Unity and Unreal?
So because of the refraction, and because we didn't have time to do a custom render pass, the output from Unity has the Unreal background in it, but ideally, for sake of latency, we would output an alpha mask with Unity, and then only what you would see refracted would have the extra latency added to it. And so that was something that we already mapped out. Or if we had opaque particles, then we could do that. But the alpha channel is fully functional in any case, and we're actually using it for the particle data as well.
In our sorry for monopolizing.
No, go ahead.
Is Unreal Touch and Unity, that chain, is that all on the same machine, or are you passing?
No. Oh, yes.
Passing between the machines.
Yes, yeah. That's the key. That's the key part of this, is that Unreal has its own server and its own A6000 Ada NVIDIA GPU. The Touch Designer particle simulation has its own GPU. And that is also doing the machine learning depth estimation, though if there was more room in this rack, we could have put another server in there and had that dedicated to the depth estimation, higher fidelity, send it over SMPTE 2110. And then the compositing machine is also running in Unity doing fluid rendering. But that could also be separate.
What's your hit in terms of latency on each of those as they're passing this video around? Like, you don't have to know to the
I don't know it offhand, but I know in the cases that we're using Spout, it's about a frame, and then the SMPTE 2110 streams don't seem to be more than that either, and we've got a pretty good indication of it in terms of how responsive the interaction is in the fluid when you step into into this area. Oh yeah, and here's the signal diagram.
One sec.
All the PIXERA have RiverMax cards, or it's just
They're Bluefield cards, so yes, yeah, they're the same thing, and they're Bluefield 2 cards, and PIXERA has done a lot of great work in integrating the Bluefield cards and verifying that everything is working, and it's been great to work with.
So the context of this question is kind of the cost curve of 2110 equipment. For the Brooklyn Mirage project, you said you didn't intend or set out to do 2110, and then you did.
Mm-hmm.
So I guess the question is, like, what were the minimum pieces, and if you're able to share maybe a budget and some of the specific equipment that you were able to pivot to, and also you mentioned some of the supply chain issues. Like, I'm really curious how in that kind of environment you were able to, or did you just have 25 gigabit switches lying around already, or how were you able to procure that?
Oh yeah, so the one thing that we did already have in hand was a Mellanox switch with 1600 gigabit ports, so 1.6 terabits, and that was really the only item that was difficult to come by, and even with our partners at Panasonic, they were like they couldn't get one at that time. At least not for the time frame that it was needed. So that made a bit of an exception at the time that made it easy. But we priced out like 5 different solutions from I won't name the names, but all the usual suspects, and the 172110 system came to about half in terms of the total cost, and then certain things that would have made the system have any sense of flexibility, like large SDI matrices, weren't available at all. So it's like we could have made it work without 172110, but it would have cost twice as much, and also it had a far less flexibility, and there's some I have a background as a network engineer with voice over IP systems, so that also helped, but it was more of its like not having the fear to jump into it, and the technical director at Brooklyn Mirage, Stephen Weicker, also had some background in network, but it was like all of the problems that we had weren't, it's like, we could have taught an intern about configuring the network, but the problems we had were things like lead times on dongles and flashing firmware on dongles. That was the transceivers for the SOPs. Does that answer your question?
Okay, cool, everyone. So we have a 20-minute break program now, and you're welcome to go over, and all of the softwares are running in the lab area. So if you want to maybe go over in small groups, we can go into greater technical depth. But yeah, we'll come back in 20 minutes, and we have another group of speakers before lunch. Thanks very much.
Thank you. Thank you.
So if you could have a seat, we have another amazing speaker for you, and we'll bring this through to lunch. So if you can take your seats, we'd very much appreciate it. Fantastic. Wow. Okay, cool. Thanks, everybody, for being so agreeable. So really happy you got a chance to hear from SmileSoft and see the sandwich. We encourage everybody to come and engage at the technical level throughout the day. But kind of switching gears now, we are really excited to welcome Marty Henning from CT. We invited Marty to speak because he's somebody who's been using ST2110 in practice on shows and really has an interesting perspective, I think, as somebody who's brought this technology into his workflows in the live event corporate show space in a really interesting way. So I hope his talk is really informative, inspiring, even though it's not about PIXERA, but that's just fine. So, all right, everybody welcome Marty Henning. Thanks, Marty.
You guys hear me? Hello? Check, check. Green lights on, anybody? Check, check. There we go. All right. Thanks, Connor, and thanks to the PIXERA team for inviting me to participate in this event. As Connor said, my name is Marty Henning. I'm the VP of Solutions Engineering at Creative Technology. Part of my job is leading the IP Transition Initiative, which of course includes SMPTE 2110. Along that journey, I spent a lot of time trying to learn how to deploy this technology in a live event environment. Hopefully today I'm going to summarize the hundreds of hours I've spent for you guys, but I did want to take a moment and thank the gentlemen that are listed on the slide here, Ryan Morris, Gerard Phillips, Robert Welch, John Mahot, and Wes Simpson are all giants in the field of 2110 IP video. If you've done any reading at all, you've probably seen some of their presentations either at NAB or the Video Services Forum. But again, I've found the information that they've shared tremendously helpful, and a lot of what you're going to see today is influenced by talks that they've given. So in this session, as I mentioned, we'll look at the strategies for designing and deploying 2110 networks in live event scenarios specifically. We'll talk about the topologies. We'll talk about multicast management between layer 2 and layer 3 designs and the protocols used there. We'll discuss tools for automation and monitoring, how those things can simplify the deployment and management, and then finally take a look at the role of software-defined networking in 2110 deployments. So first things first, you have to design your system before you can build it, certainly the easiest order to proceed in. And the number one priority is understanding your needs and then building your network to suit rather than trying to run it the other way. Management, not only for your switch configuration, but also for in-MOS routing and control. You need to make the decision if that's going to be in-band or out-of-band. That decision could possibly be dictated by the devices that you choose to use and the features that they support. One of the key tenets to keep in mind is you always want to avoid a blocking architecture. And basically, that's ensuring that every device can utilize its full bandwidth capability and the port that it's connected to, and that in multi-switch architectures, you don't create essentially a bottleneck where you could have a traffic jam. Room for expansion, of course, whatever you're going to deploy today, especially in live events, is not going to be the same as what you have to deploy tomorrow. So you have to keep that in mind and make sure that the system that you design has the flexibility and the space for that future expansion. And finally, keep it simple. There are a lot of bells and whistles. There are a lot of different things offered by different vendors that sound really great and whiz bang, but you again need to take a look at your needs and understand what it is you're trying to accomplish and what's the bare minimum you need to get there, keeping it simple, keeping it easy to manage, and easy to update. So first up is the topologies. The way you choose to architect the physical layer of your network is going to influence the resiliency, how scalable it is for future growth. We'll look at a couple of the common ones and talk about some of the advantages and trade-offs with each. So first up is monolithic or flat or collapsed. It's the simplest topology. It's literally one switch. Every device is directly connected. Flows go in, flows come out. Assuming that the ports, the individual ports bandwidth match or exceed the device port bandwidth, it's inherently non-blocking. It's relatively easy and simple to configure. And this is probably where you're going to want to start in your lab as you start developing and testing. You want to keep it as simple as possible, reducing the variables, and making sure you can focus on the functionality rather than trying to program an extremely complicated network. Of course, one of the greatest features, particularly in live events, of 2110 is the inherent redundancy offered by 2022-7. So as soon as you move from that lab into a production environment, you're likely going to want to transition to a dual core. So this is essentially the same as the monolithic network, except that everything is doubled. You've got red and blue switches. The traffic is segregated. And the senders and receivers are participating on both networks at the same time. So if there's a link failure or packet buffering congestion, the receiver is able to reassemble the stream from packets on the other network and play out uninterrupted. So again, this is relatively simple. You've just doubled the switch counts, but this is where I'll say the magic happens, or part of the magic happens, by adding in that redundancy or hitless failover to your network. Along the way, you will undoubtedly encounter nodes that are single-homed, so a single network connection. They don't have the ability to work on two networks, and you want to be able to include those in your network without sacrificing the redundancy in the other parts. So you'll often hear this referred to as a purple design or a purple switch. The idea here in the drawing is that the purple switch aggregates the flows from both the red and blue core and makes them available to the single home devices in the purple layer there. As your network grows, you'll find that a single switch topology may not be the right fit for your environment. There's a couple of reasons for that. One can be geography, having to bring cables directly from every node all the way back to the core might be prohibitive if some of those devices are located far away. You can obviously save a substantial amount of bandwidth by aggregating devices to leaf switches, and then those leaf switches, of course, uplink back to the core. The other thing you need to consider is the efficiency of your port bandwidth utilization. Oftentimes your core switch is going to be 100 gig, 200 gig, 400 gig switch fabric, and if you're plugging in a bunch of 1 gig audio devices, you're going to eat up those big ports really fast. So being able to aggregate the lower bandwidth devices into an edge switch is a lot more efficient from a hardware perspective. You do need to start to be careful in this situation because it is possible to create oversubscription of a link. So in the links that connect the leaf switches back to the core, depending on the nodes that are connected to each leaf, the bandwidth requirements in total could exceed a single uplink bandwidth, and you could end up with a failure induced by trying to fit too much down the pipe. And finally, sort of the ultimate architecture design is what's called spine and leaf. This is an enterprise architecture. It's common in data centers and broadcast network facilities now that are running 2110 networks. There are multiple redundant links between all the different switches, and you can see there's no longer this air gap red and blue design. Everything is interconnected so that if you lose a core or a spine switch, you still have access to both flows, red and blue, across that fabric. Things start to get really complicated here in terms of traffic management, and often if you're going to go to this level of network design, you're going to want to deploy some sort of software-defined network management, which we'll cover a little bit later. So now you've picked your network design. We'll talk a little bit about the traffic and how you're going to manage it on that network. I expect everybody here is fairly familiar with this, but there's three primary types of traffic. Broadcast, one to all. The sender creates a packet. The network sends it to all the devices on that network. Unicast, sender sends information directly to a single receiver. And then multicast, one to many, sender sends one packet, and then the network sends it to all the interested receivers. Before we get too much further into traffic, I would just want to take a quick second. I know there's other presentations on PTP, but PTP is the most important traffic on your network. So when you're in the design process, you need to keep this in mind, and you need to make sure that your PTP traffic can get everywhere it needs to go, and in the event of a link or switch failure, that you can still maintain consistent timing and all the devices can still reach the same grandmaster. So in this diagram here, you'll notice the cross connects between the grandmasters at the top and the core switches. And it's really important to design your priority values and your port values to create consistent BMCA results, as well as a predictable failover behavior. So if you lose one of those links, you need to be certain which device is going to take over next as a grandmaster, and that all the devices on both red and blue networks can sync to that same grandmaster. All right, so as I mentioned, in 2110, every media flow is mapped to a unique multicast group. This is the most efficient form of moving this data across the network, which we'll talk about here in a minute. But essentially, the multicast address range spans from 224 up to 239. There is an RFC, if you care to dig it up, so 5711, that identifies the different segments of this multicast range span and their different uses. But as you can see on the graphic, that first little block is defined as a local subnetwork and by default is not routable. And it's used for control protocols like IGMP, PIM, OSPF, and MDNS. So the next group there, the inter-network control, is routable, and that's where your PTP traffic is going to reside. There's some more bits in the middle there that are assigned to various use cases, which may not necessarily be implemented on your network. But two that I want to highlight here is the 232 range for source-specific multicast, and 239, which is specified as private use for internal organization traffic. The reason that those ranges are relevant as you move into your multicast address scheme, you'll find that you need quite a few of these. Even a simple 8x8 gateway device can have upwards of 3,000 multicast group addresses between the senders and the receivers. So coming up with a scheme, how you're going to allocate this address space is pretty critical to making sure you have a functional network at the end of the day. It's very tempting to try and design an IP address scheme that allows for human interpretation. So being able to look and say, okay, well that is in location 1 and it's this type of device and it's on the red network and it's a video flow. In small network, that works just fine, but in a large network, it's impossible to maintain. That type of scheme is extremely inefficient in terms of allocation of addresses, and you'll find that there just aren't enough in the space to maintain that kind of scheme. So the best practice is to use structured addressing in one of the ranges that I specified, the 232 or the 239. The other address ranges are usable, but you need to understand the type of traffic that's intended to be there and determine if that's going to be an issue on your network or not. When I say summarization, the idea is that you want to group your address ranges for different things together in a way that they can be summarized by a larger single address. So in this example, your red video is 239.0.0.0 and a /14, which takes you up to 239.4. That next /14 is for audio, and then similarly the next is for metadata. But then that entire range can be summarized as 239.0.0.0.10, which comes in handy when you're doing the switch configuration, whether that's setting up the rendezvous point in PIM, or if you're creating security ACLs to prevent red flows from getting into blue switches in a purple hybrid topology. This technique, obviously this specific example here is for multicast destination group addresses, but the same technique can be applied on your IP source addresses to sort of group your devices on the network in a way that they can be summarized for the same purposes for ACL and other routing controls. All right. The magic that makes multicast not broadcast on your network is a protocol called IGMP. There's two parts to that. One is the IGMP snooping, which monitors the multicast traffic. IGMP joins and sends the packets only to the interested receivers. And then there's the querier, which is the what's called the subscription agent, and periodically sends out requests to make sure that the devices that are receiving multicast are still interested and they haven't left the group and didn't send the leave message. So essentially it's the cleanup process to make sure that you're not sending multicast out places that it's not required. IGMP now has been around for a while. The latest version, IGMP v3, adds some functionality called source-specific multicast. And what this does for you is it lets the receivers specify which specific source that they want to receive a multicast flow from. It's possible in a network that you could have one or more senders all sending to the same multicast group. In a 2110 environment, that's not desired behavior. And without IGMP v3, if a receiver tries to subscribe to a group that has multiple senders, they'll get both flows from both senders, which can lead to port saturation and lost packets. IGMP is backward compatible to earlier versions, but you need to be aware that it's the lowest common denominator, and if there are IGMP v2 devices in an IGMP v3 network, the whole network will default down to the v2 standard. So you'll lose that benefit unless all the devices can participate at v3. All right, so IGMP is fantastic and does exactly what you need it to do in a layer 3 environment. And on a single switch, it's perfectly appropriate to use. One of the key things that you do need to be aware of with your multicast addressing scheme in a layer 2 environment is that the multicast group IP addresses are translated to MAC addresses in a layer 2 environment. And because of the way that's done, you end up having 32 possible layer 3 IP addresses that map back to the same layer 2 MAC address. So you'd end up in a similar situation as you would with v2 IGMP, where you have a receiver trying to request a specific flow, and they're getting flows that they didn't intend to get, which could again lead to oversubscribing the port. The other issue with IGMP and layer 2 environments specifically is what's known as flooding to the querier. So in a layer 2 environment, IGMP, there's a single querier that's elected among the switches. Typically this would be at your core switch. So in a dual star topology, all of the senders on a leaf switch, there really should be a graphic here. I'll take that note and see if I can add it. All of the senders would have to flood their traffic back up to the core, whether it's being used there or not. So you're consuming bandwidth, even if the receivers are on the local switch, you're consuming bandwidth on that uplink, which could ultimately lead to issues or require additional bandwidth in that uplink to deal with your other requirements. So the way to correct this issue is to move to a layer 3 environment in a multi-switch deployment. Excuse me. The benefit here is the elimination of that flooding. IGMP is no longer responsible for managing that traffic between switches, and you can make sure that only the flows that are required are moving across those links. This is a much more scalable way to manage the traffic as well. As you get into larger and larger deployments in a layer 2 environment, your failure domain is across the whole fabric. So if one person plugs in one misconfigured device on an edge switch somewhere, you could take down the traffic across the entire network. So by designing some layer 3 links into your topology, you can break that failure domain down into smaller segments, which reduces the chance of a failure caused by a misconfigured device. So in layer 3, the protocols are slightly different. Depending on the topology, you're still going to be using IGMP in some way. But the two big ones that you need to be aware of here are PIM, specifically PIM sparse mode, which manages the multicast routing across the subnets in much the same way that IGMP does it in a layer 2 network. And then OSPF, or Open Shortest Path First, which automates the routing table updates. So as your network grows, the routes between the different segments don't need to be manually created in every switch. There's some design flexibility in a layer 3 deployment. The simplest way to implement this would be to change the links between your core switch and the edge switches to layer 3. But then you can still use a layer 2 VLAN for all the access ports on each switch that all the local clients are connected to. You've, again, localize that failure domain to an individual switch, but you can still use single DHCP range and an IGMP to manage the devices on each switch. And then you can take that as far as configuring each port on the switch as its own layer 3 subnet, which again shrinks down that failure domain and gives you a little bit tighter control via ACLs or the like of exactly what's happening across your network. I just mentioned IP addressing, and in a fixed facility, creating a scheme that uses static IPs is extremely straightforward, both in layer 2 and layer 3 environments, because the devices rarely move. You plug them in, you turn them on, that's where they operate, and it's not a problem. In live environments, static IPs outside of a single switch layer 2 deployment don't really work. As equipment moves around between switches, especially if there's any layer 3 links involved, you're either looking at a lengthy shop prep process to configure individual nodes to work correctly on the switches or ports they're going to be assigned to, or you're going to be trying to make those changes in the field. In a live event environment, using DHCP for that purpose streamlines that deployment because now it doesn't necessarily matter which port a device gets plugged into, because using something like DHCP option 82 will allow that device to get its IP based on where it's plugged in as opposed to what device it is. That was the management in a nutshell, I'll say. Obviously a lot of information, but as the networks get bigger, again, it's key to make sure that you have a strategy to keep track of addressing schemes, ranges, and then the traffic management itself. One of the things that you can do to streamline that process is employ some automation. Anyone that's ever configured a switch via CLI understands how tedious that can be, and there are several benefits from automation. Consistency, obviously reducing human error, the efficiency, much faster deployment and updates, and then scalability. When you get into multi-switch networks and you need to make a simple change, doing that across half a dozen switches ends up being fairly time-consuming. And then, as I mentioned, initial switch provisioning. So if that's configuring the VLANs, your router interfaces, and all the protocols, you can have that decided in advance and then deployed in an automated fashion to each of the nodes. Configuration checks. This is really great for a live event environment. You send a switch out to a gig. When it comes back, you're not really sure what may have happened to it on site. You set it up with the automation agent, and now you can compare the intended config with the current config and either revert those changes or then adopt them back into your master config. Software updates and patch management, and then of course backup and restore configurations are all things that can be streamlined via automation. There is certainly no shortage of products that can do this. Some of them are manufacturer specific and proprietary. I'm not selling anything on Ansible. It's actually open source. I just wanted to list it here as an example. But it's extremely effective for this type of work. It's agentless, which means you don't need any software installation on the devices to make it work. It's based on what are called playbooks that can be broken down into very small components and then combined to create complex configurations. And then multi-vendor support. It's not locked to a specific vendor and can be used not only across your network infrastructure, but potentially across your endpoint devices as well. In any media network, it's not enough to just build it and hope it runs smoothly. You have to actively monitor its performance, anticipate potential issues, and be able to respond quickly when something goes wrong. It's not just about visibility, but it's also being able to understand what's happening in your network at a glance, and then being proactive rather than reactive. First bit of that is the data collection. Your switches produce a tremendous amount of data between logs, and then most often they'll have some implementation of SNMP, or the Simple Network Management Protocol. This has been around for a while, but it's still widely used and very reliable. And you'll be able to get critical metrics out of your switches for port state and link speed, optical power for SFP devices, and then frame statistics as well, CPU, memory, fans, temperatures, etc. And then somewhat newer version of that is called telemetry. It's available on some devices, but rather than being a polled update or maybe a trap set on a specific condition, this is sort of a continuous data stream that comes out of the switch. And again, gives you those real-time metrics that you can then base your visualization system on. So you've got the data. That's the first step. You've got it aggregated. You've pulled it out of each of your individual switches. But visualizing that data is really where the magic happens. You're turning all of that raw data into information that you can use to understand the health of your network. Again, there's a multitude of tools that are available here, from open source ones to vendor specific and very proprietary ones. A couple of the ones that we've got experience with, Prometheus and Grafana make a great stack to collect those metrics and then be able to create unique dashboards to display it. Zabbix is another one that we've used. It's integrated and can run agents on devices that aren't necessarily SNMP enabled. But the key is setting up alerts and thresholds for all of the critical metrics. It's nice to have the pretty graphs and the dashboards and the visualizations, but by setting the alerts and thresholds, you can have higher priority visibility for things that are problems. So if that's minimum power levels on SFPs, if that's fan temperatures, or fan speeds or CPU temperatures across switches, having those items have an alert box or an event page where you can see immediately that there's something that needs your attention. A lot of times, or a great example of where this is saved a deployment. We lost a laser in an SFP. The signal continued uninterrupted because it was just running on the other side of the network. But because we got the alert on the dashboard, we were able to send somebody out, swap out the SFP, get that link back up before everybody knew there was a problem. All right, I mentioned software-defined networking a bit earlier, and SDN really complements everything that we've discussed so far. Monitoring, automation, control, and management. As your network gets larger, this is something that can help keep it manageable, even in the most complex environment. Essentially, this is a centralized control server that sits on top of your network. It sits on top of your broadcast controller, and it takes over some of the functionality that is traditionally handled by the routing protocols like PIM, IGMP, in the instance of multiple uplinks between switches. The default network device behavior is to use a hashing algorithm based on the source and destination IP to decide which link that traffic goes on. It's not bandwidth aware, and depending on the combination of flows, it could very easily oversaturate one of the links. And so what SDN does is it adds some intelligence to those functions to, again, help you manage and control those flows on the network. As I said, it's bandwidth aware, so it knows that your uplinks are currently subscribed at 50% on one side and 80% on the other. So it's going to put any new flows on the link with the lower utilization. It's also aware of the network switch states, and if you're to lose a switch or to lose a link, it'll intelligently reroute those flows across the network. And in another more advanced use case, it can also be used to manage network address translation of flows, which essentially means you can manage the receiver's traffic without the receiver knowing something has changed. Essentially, the receiver's always subscribed to the same multicast group, and using NAT, you're just controlling what's getting in there. See, I think I covered a lot of this already. The bandwidth awareness, the deterministic routing, rather than the routing protocols picking an arbitrary path through the switch fabric, you get a little bit more flexibility and control there. And then, of course, scalability. As that network gets larger, being able to manage it more easily. There are, again, a number of providers in this space. Some of them are manufacturer specific, and there are others that are a bit more agnostic and can operate across switch brands. To kind of sum it up, the network design matters. Picking the right topology, making sure you understand where you're trying to go with the network, and incorporating those things into your design. The multicast management and choosing between layer 2 and layer 3 schemes, and then making sure that you've taken the appropriate steps to protect your PTP traffic and ensure consistent performance in a failover scenario. IP addressing schemes and assignment, making sure that you understand, or make sure you use the summarization to allow for easier configuration. Having a solid plan in terms of source IP assignments and management. And then adding automation and monitoring to maximize your visibility and your efficiency across the network. And then finally, software-defined networking and the enhanced control that's offered there can be, depending on your topology, SDN can be almost a required component in order to maintain manageability on that network. So I think that's it. I think we got a couple minutes left if there's any questions. Again, I know that was a lot, and I was trying to summarize all of these different bits that I've gathered over the last year and a half, 2 years from various sources. And I'll be honest, this is the first time I've delivered this presentation, so happy to take any feedback, anything you guys felt was missing or wasn't clearly enough described. I'll be happy to take that and implement it for next time.
When you were talking about the multicast address, overlap stuff, did you come across the reason that happens? Because it's a great story.
I mean, other than the fact that somebody decided that you didn't need the first 9 bits.
And then the reason they came across that is like it was being developed in university for research purposes, and he couldn't get enough grant money to buy the entire IP space to block out the multicast because they would only give him so much money. So they bought like one thing and split it between 2 projects. So now we're stuck with this very strange MAC address multicast mapping thing because of some university's budget constraints back in like whenever they were figuring that out.
That's pretty good. I think I might add something about that.
Hey, I'm just wondering how this has impacted your approach to like prepping jobs and like bringing them out in the field. Or, like what parts of it are staying at home now that a lot of this is software defined and network based?
Well, we actually made the decision to send everything that manages the show to the show, but we've added remote connectivity into those systems. So essentially, as soon as the core rack is powered on, it phones home, and we can get access to it wherever it is, which means that we have that visibility in case the on-site engineers are having any trouble. We can very easily troubleshoot that with them and get them up and running. As far as impacting those deployments, the goal for us in live events is to not necessarily need a network engineer on every deployment, which means that the system has to be plug and play enough that anybody that can construct a solid layer 1 network, they know where to plug the wires in, can get this system up and running, and then it's up to the engineer to manage the routing across the system.
Can you describe how you were using DHCP option 82? Like feel it like it gives you an IP address based on where it's plugged in. How are you deploying that? How does that make your lives easier and stuff like that in the grand scheme of setup?
Sure. So what option 82 allows you to do is have a centralized DHCP server as opposed to distributed across your switch fabric. So in the basic layer 3 implementation, each switch has its own layer 2 VLAN that all the nodes exist in, and there's a DHCP server on each switch for each of those VLANs. If you start turning every port into a routed port, now you need to create and define DHCP lease information for each one of those ports, which is possible, but again, it requires that to be managed at the switch level by using option 82. When the device plugs in and that DHCP request is received, instead of being dealt with locally on the switch, it's sent up to your centralized server where you can maintain single configuration.
How is, I guess the answer today is going to be very different from the ideal future. How is multicast subscription handled, where you've got like a video mixer that wants to subscribe to a bunch of multicasts that are coming in from different cameras or graphics machines or whatever? Like how do you handle the client side of that equation of what's going to receive a multicast?
I think what you're asking about is the broadcast controller, right? You're like how do you tell your receivers what they should be listening to? Is that your question?
It's more how do you subscribe to those on the receiving end? So you say, all right, I've got 40 feeds coming in from different sources, graphics, cameras, et cetera, and they're all multicast. They're not unicast. They're not broadcast. How do I, as the receiving device, say I'm interested in these 7 multicast feeds, so please route them to me?
So there's a combination of NMOS and the broadcast controller managing those devices via NMOS. So all your nodes, when they come on the network, will register themselves with the controller, the NMOS registry that is then accessed by the controller. So the controller is aware of all of the senders and all of the receivers. And then it's a lot like a baseband router at that point, where you select a receiver, and then select the senders that you want to go there. And those can be, depending on the control system, you can create containers that contain multiple flows. Obviously, you can combine in a single video receiver or display receiver example. You'd probably have one video, one audio, and possibly metadata. You can package those in a container, even if they don't come from the same sender, and send that in a single route.
I have a question. I noticed, everything's still IPv4 here. Is IPv6 still kind of in a AV isn't quite there yet because we're not at enough devices to need it? Are we moving in that direction? And, how much more complex does all of this get if we have to switch over to IPv6? How does that factor in any of the gigs you're doing or any of the projects you're working on?
Absolutely. So the IPv6, in my opinion, the primary detractor is the lower human readability of the address. And in the deployments that we're talking about, the source and destination address groups are in the millions. So you'd have to have a very large deployment before you started running into to capacity issues in that way. So even in enterprise networks, there's been a lot of resistance to transition to IPv6 just because of the complexity involved. And I think there's still a lot of people that are under the opinion or mindset that IPv4 still works for us. And so until they have a real impetus to do that change, I don't think we're going to see widespread adoption. And I think, as typical, the AV industry will lag even behind that.
Excellent. Well, thank you so much, Marty. Really appreciate your insight. And, it's actually a really good segue into our next speaker. Alex Pendleton from Netgear AV is going to talk about IGMP+. We'll keep the networking theme going, and I had a really cool conversation with Alex at LDI about how to handle uncompressed video on a multicast network, and he's going to keep the network trend going and share with you a little bit about how Netgear is solving those problems. Maybe I'll let you introduce the handheld halfway through if the stream audio is not good enough.
Test.
All right. Okay. Well, that was actually good that I got to follow Marty, because everything that he said, I'm going to reverse. Not everything, of course. A lot of the things that he explained in the enterprise is going to be required, especially with PIM and multicast addressing and things like that. But my name is Alex Pendleton. I am the Pro AV Design Manager of the Pro AV Design team at Netgear. I've been at Netgear for 15 years, so you can call me the ghost of Netgear past. I definitely have seen a lot of failures that this company has done, but I've also seen a lot of successes, and I like to talk about them both because that's how we got here. Our successes were literally predicated by our failures. So I call this presentation SMPTE 2110 and IGMP+, and what to kind of expect from IGMP+, which is our core fundamental. It's our core system of multicast management in these designs. It is small, medium, or in the large enterprise capability. But first, I'm going to give you a little history lesson of how we got here. So who's heard of Aptivision? Raise of hands. Okay, a couple of you. So Aptivision was designing a chip in July of 2015, and they were buying Netgear switches already, some of our M7100s, 7200s, really terrible multicast switches that we didn't really offer for that. But they were using it, very complex configuration to get it to work, and we found out that they were purchasing it. And luckily, we had a new switch series coming in 2016 that was going to bring the price of 10 gigabit down significantly. And so we released the M4300s in 2016, which was going to support their next evolution, which was their SDVOE Alliance. And Netgear became a founding member of the SDVOE Alliance based off of our conversations with Aptivision and the other founding members, Sony, ZV, Christie, Aquantia, and of course Aptivision. Now we were getting added to a lot of large-scale SDVOE high bandwidth networks at that time, and we ran into a scaling issue at layer 2. Part of what Marty was talking about in his presentation, this issue that we ran into was that you couldn't get to a certain size at layer 2 without causing oversubscription everywhere. Essentially all this flooding was going back to the courier, going back to the core, and so we created a new system essentially called iGMP+. I'm going to talk a little bit about that a little bit later. Then, in November 2019, again, we were in those large networks, and the largest bandwidth we could do was our 1.9 terabit backplane M4396X. And that was it for SDVOE. We needed something bigger. We needed something larger, because even the designs at that time required 100 gigabits between network segments. So in 2019, we launched the M4500 series, which is 2 series that became our core switches, our aggregator switches. Then, in January 2020, it was announced that Crestron had approved our 1 gig solution, thanks to the work of Devin Kress, got us in the doorway essentially with Crestron, and they finally approved us after we had been trying to get them to approve us for very long. So it was a big moment for Netgear, and we got that call in November of 2019. That led to 1 gig AV over IP, AV line switches designed specifically for AV. We brought a council to our facilities in San Jose, California. We had them tell us what we needed to do for them that would help this industry grow to a size and scale and to further along AV over IP. And that was our M4250 series. With that came a new system to configure templatized deployments, which was the AV UI. That was launched in September of 2020. We started getting contacts from people. They were like, what about lighting? Why did you leave lighting off of your profile list? And we were like, shh, okay, we'll fix it. And we created our lighting profile, which 2023 Super Bowl, we ran the entire halftime show utilizing this profile. In October 2022, we launched our centralized management controller because we had this AVUI experience. It was a good experience to use, a lot of fun to use, but we wanted that to be in a more centralized location. So we built the Engage controller, and we used that in a development process to take those older IT switches that were used for SDVOE, the M4300s, and bring the AV user interface to them as well. Then, July 2023, we launched our next predecessor of the M4300s, IT and AV switches combined with some IT features, but mainly AV throughput because we wanted to be able to enter into the broadcast-capable switching. In January 2024, we launched our Phase 2, which came with Grandmaster and boundary clock-capable switches. We're using 2 of them here in the sandwich. As you can see, they are the centerpiece, and they go between for all of the signals you're seeing and all of the demonstration that's being done in the exquisite sandwich. So 2025, how do we do it next? Well, you can say 2025 we're going live or something like that. I don't know. It's stupid. All right, we are going to focus live events. Broadcast-capable switching is our focus for 2025. We are investigating products right now that will be designed specifically for these environments, including these switches that we have to enhance the software that uses them. And that is going to be our process as we move forward in this year. As you can see, we've amassed over the last 8 years, starting in this business, a huge partner list. We send them their stuff, or our stuff, they send us their stuff, and we test it in our labs, and we see exactly what works and what doesn't, and then we work it out as best we can. So if it requires a profile, we'll put a profile in. It's a huge, huge list. This is as of October 3, 2024, but it's getting even bigger Thanks to Devin. Again, I'm here with Devin. He's the director of our business development. I don't want to shy away from him because he's a big reason why we are here. Just as the latest firmware right now, these are the latest profiles that just went in. And these are really easy to set up. Get into the interface, select the port you want, drop the profile in, start connecting devices. And as Ryan will tell you, when he went to configure this for this system, he literally configured one profile, hit go, and we were ready to rock and roll. To give you just the end of this switch framework, the one AV line is our 1 gig with 10 gig uplink switches, 13 in total with the 2 little desktop dudes. The M4300s are in their product sunset. I literally chat GPT to end of life. It sounded so permanent. It sounded so horrible, right? End of life. So I did like, what are other words? And it said product sunset. I was like, oh, that's nice. It's just on its way over a cliff, right? And the M4350s to replace it with 100 gig uplinks. Essentially same IT features of the M4300. So you have stacking, you have non-blocking architecture, all of these added items, plus SMPTE 2110 capability with a SMPTE 2110 profile. And then we have our aggregator switches, the active core MLAG systems that we've built many systems all around the world with the M4500s. Okay, so I'm going to cover in this slide essentially what IGMP Plus is, why it's important. I got to kind of give a little history lesson again. When we were doing a law firm in New York City, 1 Hudson Yards, Cooley, they had the 40th floor all the way to the 60th floor in some building. And we started on the 40th floor, commissioning each floor as we got on. All these 10 gig Aurora endpoints coming back to a stacked core of M4396Xs. And we started noticing streams on the 47th floor and 46th floor that were not destined to be flooded up there. They were not supposed to be reaching up to these floors. And not only that, it was causing oversubscription of those links, so you saw dark screens. Sometimes you'd see an image. So we were like, what the hell? So our engineers took a look, and we evaluated it. We decided to place ACLs between the segments of the network to kind of control the traffic, to control this flooding. Well, that's not going to work. That's a Band-Aid to a gunshot wound. It's not going to get the job done. So what we did is we fixed it. We gave logic first to all the switches. They now share the report between all of them. They understand where all the streams are supposed to go. And then we only allow the stream that is supposed to go upstream to the courier and to the spine switch, and then out to the edge switches. I can tell you from the 5 years that I've worked in Netgear's AV department that this is the single most unique development because the core of switching is layer 2. It wants to switch via the MAC address. Doesn't really care about the IP. We sure give it layer 3 routing is like sprinkle pixie dust on top of the switch. But truthfully, the core of the chip is the MAC address. So we keep a system at layer 2 without the erroneous flooding that Marty talked about. And we are able to scale the network to the size. As soon as we applied the firmware at the Cooley Law Firm, boom, worked. And then we knew we had a system that could scale, and then that led to the World Health Organization, numerous universities around the world, stadiums that are going up all over the place, and different deployments, small, large, and medium, and enterprise. With that system, you need an easy way of connecting switches together, so that's what our auto trunk and our auto lag features. You connect the switch together, 2 Netgear switches, we send a little hash over there. Are you a Netgear switch? It replies back, yes, I'm a Netgear switch. And then we trunk those VLANs together so that we allow them to traverse across the trunk link. Then, if we add an additional link for redundancy, we go ahead and a linear increase in bandwidth, I know. You do increase the links between the 2 switches automatically. And this works very, very, very well, okay? And it's an out-of-the-box configuration by default on all of our switches. Another enhancement that really needed to be done that we found about 2 years ago, aside from our IGMP Plus, is we needed an interoperable QoS platform that solved all QoS problems, not just one for one system or one for another system. We needed everything to work together in the same network, including AVB, SMPTE, any of the QSys environment with Dante, NDI. All of these things needed to have their QoS tuned, and we did. We created a platform that stopped the interactions from happening from the different systems and allowed for the traffic to get onto a different lane in the freeway, so it's prioritized and it doesn't have to get jammed up with the residual traffic. To cover the differences between where we were and where we are is our IT deployment on the left was our very common in our data sheet that this is what we expect from the IT world. And you can see that that system requires VLANs and restrictions and all of that. And then you look at the AV network, everything interlinked, everything intersecting, all of the endpoint nodes being connected to that, coming back to the core, having redundancy built in, but you have an open communication for discovery. Because those systems are all in the same broadcast domain, they can discover, be found easily, and managed very easily. And our IGMP Plus enhancement keeps the multicast localized to every switch until requested. That means that the bandwidth is also available upstream. So the scale of these networks will only continue to get bigger as we go, and we see these happening. This is actually the Visa network that we did at Mission Rock. This is their headquarters, a double-tier MLAG design that we built. Okay, so let me cover how we do PTP. It's not different from the standards, but I just want to kind of explain it from our perspective, because there's some switches that do transparent clock, and that's what our default is, PTP transparent clock. We also support PTP v1. We'll flood that all over the network. The devices that will do that, you manually set your offsets. But PTP v2, we will interact with those packets, and on all of our switches, we have PTP v2 end-to-end transparent mode enabled. The way this transparent mode works is if I take the laser pointer here. Awesome. Okay. So ingress, that's Netgear fancy speak for coming into the port. We're coming into the PHY, which is a coalescer that grabs all the packets and then forwards them onto the Mac controller. This diagram's incorrect. It actually shows 2 Mac controllers. It's one chip, all right? It's just going into the same chip. As it goes through that chip and it begins to come out the PHY, the egress port, as we say in the networking world, we stamp it. We update it right here into the correction field with the amount of nanoseconds that it spent inside the switch. This is what Connor was talking about in his presentation. Essentially, when you see the amount of time that it takes for you to send video, that 1.2 milliseconds, imagine the amount of nanoseconds that we can stamp a packet at if we're switching at microseconds. So yes, the variance is important for the Grandmaster and the client endpoints to be in sync. And so that's what we'll do with the PTP-v2 packet. We'll update it as it leaves the switch so that the Grandmaster knows. So in the clocking domain, essentially, you have your Grandmaster and your boundary clocks. This is specific for ST2110, right? Every boundary is technically a Grandmaster, and every Grandmaster is technically a boundary. It's whoever has the lower priority time and whoever wins the best master clock algorithm in order to determine who is that Grandmaster. And they do this via the announce packet. They all announce at a certain interval. They all evaluate each other. Whoever's best clock, boom, becomes Grandmaster. Then Grandmaster syncs to the boundary. The boundary will sync to your ordinary clocks or your endpoint clocks transparently, and it will keep those in sync as the Grandmaster for those devices. That big sync packet also for PTP-v1 and your Grandmaster, as well as PTP-v2, is what ordinary clocks are going to be looking for from the boundary clock. If you were to look at this in nature, it's kind of like a coyote call, right? About 9:30 p.m. in California, you're going to hear them all yapping in the mountains there. And that's them announcing that they're still alive. I don't know if you guys knew that, but coyotes, they make sure everyone's alive. If one's not, then the females become fertile, and then the males reciprocate the species. So, so essentially, that's the way I call the Grandmasters. Essentially, they call out to each other, and they all respond, and this is how you get your best master to be selected. That announcement interval is the amount of time that Grandmaster has to wait till it becomes the master if no announcement message is received. So the transmit of the announcement message, if an announcement message is received, then we start doing a data set comparison of the best master clock algorithm, which is a subset of features that essentially is priority 1, clock variance, steps removed is the final one, but priority 2 is also in there. And then we determine at that point or generate the announcement message to essentially assign the PTP master. So the master port, once you determine who the master is, if it's the boundary clock and the other switch is the master, we will go ahead and slave that port to the master, and then that master switch will be the ordinary clocks as well. So let's get into the SMPTE standard and which switches we offer currently. Now this is just the first offering. This is us sticking our toes essentially into the SMPTE waters, okay? This is not the end. I can tell you that right now. We will come out with a lot more in the future. Of course, I'm a public company. We can't give you roadmap discussions because we're, whatever. Anyway. All right, M4350 16V4C. Okay, that's what's currently in the rack right now. It's a 16-port, 25 gig switch. It has 4 100 gig uplinks for your Panasonic Keros to plug right into it. You also have the M4350 40X4C, which is a 40-port PoE++ switch. Also has the Grandmaster capable switching. But all of our switches can be utilized, essentially, in a SMPTE environment because we have PTPv2 transparent clock. In fact, at the Ames booth, Jean Lapierre from Matrox was able to switch between IPMX and SMPTE just by enabling one of his endpoints to be a Grandmaster. No change to the screens. Screens continue to flood. You didn't see any modification to the video. It's such an amazing demo because he's switching literally ST2110 IPMX as he goes through on his stream. So yeah, this is done actually not with any of the switches you see right here. It's actually done with our M4250 series. So it's a 1 gig system. So the way we look at our place, essentially, in the grand SMPTE environment, and you can see the list up here is that best master clock PTP environment up here. We see ourselves in this type of configuration. Like you could have a passive master port, you could have multiple boundary clocks, but you'll have an external Grandmaster. Could you run a small deployment with these as a Grandmaster? Sure, that's what we're doing right now. So that's where we see it essentially happening here. Our use case number 1 with the Panasonic Keros, the different cameras, you can build a pretty sizable system with all of these devices. And all of these devices don't necessarily have to have the static mapping, right, of the multicast, which is what we've talked about in the past. In the past, we've said, you got to statically map, this has got to go here, this has got to go here. But if these endpoints dynamically subscribe, you get the same benefit because of the Grandmaster clocking and the PTPv2 transparent clocking. If you look at this intercom system, we did the VMAs recently with a company called Firehouse. 396 belt packs, all running simultaneously through a Netgear system. Some layer 2, or excuse me, M4250s, and then we had some M4350s in there as well, all working, and the M4500, excuse me. So that was another example of what we can do with our system. Another thing here is a SMPTE edge system. So again, this isn't the core switch you would put in a large enterprise network, but this could be an edge system in that enterprise scale network. So this was our first deployment. I wanted to illustrate this was a big moment for Netgear because this was our first validation test in Japan from a company named Astro. Brought us in. They had a Telestream SPG 8000 with a Netgear M4350 and a Panasonic KC100T. If you've ever heard that thing, it is extremely loud. I'm glad we have the new Panasonic devices because that sounds like a jet engine. As soon as you send this to the screen, though, it worked right away. We hit without even having to change anything on our system. So we knew we had something special. And then that led to a partnership with Panasonic, as well as our first deployment at YTV in Japan. We did the entire facility there. And so it was a very successful moment for Netgear and kind of a proof that we can enter this industry. And not only that, we can innovate using our IGMP Plus enhancement. All right, so often when I talk about SMPTE 2110 in our booths, and I talk to people that are very familiar with SMPTE 2110, they come up to me, they're like, but you don't interact with the NMOS API. So how could you possibly do a SMPTE 2110 network? So I call the big bad wolf internally is the NMOS. We support NMOS pass-through. This works for IPMX. This works for SMPTE 2110. If the endpoint registers to NMOS, we'll forward that to and from the devices that need to be involved. But you won't be able to essentially change the routes on the Netgear switch. We will rely on the endpoints to do that. We call that dynamic join. If the devices support dynamic join, then we will facilitate that very, very quickly, and IGMP Plus will protect the whole of the topology. So no API interaction. However, peer-to-peer discovery works really, really well. We did this at the ISC booth. We set up some IPMX encoders and decoders. We connected to them. They link up real fast. So it was very, very easy to do, and it was the exact same quality as a SMPTE 2110. So without further ado, this is my team. This is the group that are there available to help you along the journey to build these networks, to design these networks, and to help you see what Netgear can do for you. We are a global team led by this man here, who's the product line manager for all of our switches. You could call him the godfather of AV at Netgear. He has started us on this path, and he brought me and Derek in. And I call this the A-team. This is Stefan, Nicole, Casey, and Ryan. We have another person also, Victor, who's not pictured. And we have Michael Deck, who's coming from Ireland to cover the eastern seaboard. So we are growing this team, and we will be available 24/7 for you guys. And with that, I'll take your questions. I hope there's a lot. Yeah. Testing. Yep.
Not to put you on the spot, but
Please do.
We've been throwing around IPMX in the room, and I don't know that everybody really understands what the difference is between 2110 and IPMX.
Oh, that's very simple. So IPMX takes away the timing requirement, but gives you the exact same encoded video value that SMPTE 2110 produces. So you actually get the same value of system, same type of NMOS discovery and registration, all of the things that make SMPTE so fun to use, but takes that timing requirement out of the picture, so you don't have to have that. And that's why it's so unique, and I think it's a very fun thing to play with. I can tell you the endpoints that we got to display in our booth, we literally logged into them, they found each other, I hit link, and we were up. I mean, it was very, very simplified. And that's what we want. We want to get to a point for these broadcast networks that it's simplified. Complexity comes when you do those layer 3 configurations. You're isolating it and having to do option 82. That is the complexity that you can add to it. And for the enterprise, 80,000 endpoint systems, go ahead. But for these systems that we can build together, along with PIXERA and the rest of the teams that have come to present, I believe we have a solution that will support you all. Yeah.
I guess one thing that has sort of caused fear in us for deploying IGMP Plus is a relative lack of documentation and understanding what exactly it is. And your presentation has done a really good job kind of clearing up what some of that is. Is that information available somewhere on the internet so that we can see it? Like I remember at one point Googling IGMP Plus and finding nothing, but having even just a few of those slides somewhere would actually probably help us to explain why we are or aren't deploying that in various things to smooth over with the engineers.
That's an excellent question. We do have a white paper on our website. I can get it to you. It was actually done through our community, so the gentleman that wrote it didn't necessarily post it to our website, but posted it to our community. So there's a community link. If you did IGMP Plus white paper, you'll find it. It is our IP, though, because the companies that we are up against here didn't figure that out. They just kind of said, well, you need to go to layer 3. Well, we kind of solved that, so you don't have to go to layer 3. And that's kind of why it's our IP. So we do kind of protect it, and it is also an enhancement on top of IGMP. That's why it's not IGMP v4. right, with a new RFC or something like that. It's still interoperable and disableable and enableable in interoperating scenarios. And we've done many, many different networks where we are not the only switch in the world. I mean, the Super Bowl is a great one because we had 4 different switch vendors coming into our network and we were going into their network. So IGMP Plus had to be disabled in certain scenarios per port. So that would be the answer to that. So yes, it is a layer above what we do with IGMP v3, but it is not another version. It's an interoperable version with all different types of IGMP. Good question.
Hey, Alex. I have a question from the live stream.
Cool.
Someone is asking why there's not a 2110 profile on the M4250 switches.
We do have one on the latest firmware. So if you go to the latest firmware, there's a thing called hybrid, and you could leverage the audio AES67 or the video AES67 in the interim if you're not going to upgrade the firmware. Yes, we do have a hybrid one that is going to be on there that'll allow for that, essentially. And it's usable within our Engage controller, which we have over here, if you would like to preview it, that's running the sandwich. Sandwich. Did I say sandwich? Screwed that up. Gosh. All right, thank you guys. Oh.
Just curious about when you're explaining the slide about the QoS, how you manage to make it more harmonized. Is it a way that you could describe how you made it?
That would be pretty tough.
Yeah.
In short, we take AVB and we allow it to do its bucket, and then we globally trust its bucket. Then we take what we do with PTP and audio and video, along with some of the discovery protocols, and we class map them essentially into different buckets. Yeah, that'd be the best way to explain it.
Excellent. Oh, yeah. Well, thank you so much,
Thank
Alex.
you, guys.
Yeah. Cool. So we have some really delicious sandwiches. We're gonna crowdsource, kind of putting up the chairs and creating. We have some high top tables so we can relax and eat for lunch. And then we have a real special treat after lunch. Michael Kohler is going to give his interactive PTP demonstration. It's so cool, so entertaining. And then we'll go right into Daniel Warner. And Panasonic, and that'll be it. So we hope you can join us for lunch the rest of the day, and we'll reconvene in about 45 minutes to keep going, and looking forward to connecting with you all over lunch. Thank you. All right, everybody, thank you so much. We're about to go live again to the stream to all dozens of people watching. I think we peaked at like 40 or 45, so that's pretty good. We had 60. We had 60 people watching the stream. I think right when the Smile showed their inactivities is when everybody is around when we went viral.
Which partners? Here we come.
Yeah. So I don't know. Are we live yet? Hi. Okay, we're live. So thank you so much. Really special treat for you here. I don't think this person needs introduction. McColler is a force in the industry, and he has very generously agreed to come and do an amazing presentation on PTP that's live and interactive and hilarious. And we'll go right from that into Dan Warner. And I think just to respect everybody's time, I just sensing the vibes of the room that we'll take a quick bio break, and then we'll get right into Keith's presentation to round us out, and then we'll set everybody loose early, so we'll forego that last break a little bit. But anyway, with no further ado, Michael Kohler and his PTP demonstration. Thank you.
Cool. So I'm Michael Kohler, and I'm from Fuse Technical Group in our CATS division, which is the Center for Advanced Technology Solutions, where we lately have been building computers, both by hand and with soldering irons, which is strange. And one of the things that I've spent a lot of time nerding out about, because I kind of discovered the interest of it, is time and timekeeping in these video systems. I wanted to learn about SMPTE 2110 because I was like, ooh, the network. This is the logical future of video. So I started like Googling like, how do I learn SMPTE 2110? And like everything's like, start with PTP, learn PTP, watch these 27 YouTube videos. So I watched a lot of YouTube videos about PTP, and you know, similar to the Standing on Shoulders of Giants, I watched many of the SMPTE ones, but I also discovered a new class of YouTube influencer who are like the open source time hardware people who like build this stuff in their home lab and are like competing to have the most accurate clocks at home. And the passion of that community is what really got me into like understanding how this stuff works, because they make some pretty entertaining videos. So anyway, without further ado, I'm going to attempt to explain what PTP is and why it's actually interesting and useful. And we have to kind of explain everything about how time works, which is sort of this like human history long rabbit hole. So this is just kind of the tip of the iceberg, so I'm not offended if everyone gets bored, but there is a live demo to look forward to, and you know, maybe I'll screw something up and it'll be even more exciting. So yeah, we're live events people or performance people, and you know, everyone's like, okay, why do we care about this? Obviously, like, we need to care about the power for our systems. We care about the data distribution. Why do we care about time? And, you know, performance of any kind is time. And every part of one of these productions is really actually interrelated with timing. Music is like notes and vibrations over time. Scripts are words presented over time. A cue list is a list of things that happen in certain times. Choreography is movement in time. So, like, time is what makes performance. So as live people, we need to like remember that all of our computers are performing in some way as well during this process, and they all need to know what time it is as well in order to do things together and make beautiful music or video or whatever it is our computers are doing. And it's the key to show control. We started with cues, you know, back in the technicians being sailors days, people would whistle, and that would give you the cue to move pieces on the set. And that's why you never whistle in a theater, because a drop will fall on your head, like in Scooby-Doo. In 1953, there was like NTSC television and Genlock, and how do you keep all this newfangled video equipment in phase? In 1967, they came out with like linear time codes so that you could stamp the time in video equipment and make sure that the part you were editing was the part that you thought you were editing. And you know, there's performance control aspects based on that, so devices that follow time code or generate time code. At some point in the 80s, we had Ethernet, which is how computers communicate. And if all the computers were screaming at each other at once, not much communicating would happen. So there's timing implications just in regular old Ethernet. MIDI, DMX, these are all signals that really have timing tolerances that have to be dealt with. But they're usually dealt with internally in a device, so we don't think about it as often. So we're going to talk about horology, the study of measuring time, and how we keep time. And one of my first production credits out of school, I made this DMX-controlled clock for someone's production of Around the World in 80 Days. And I wanted to be credited as the production horologist, and they did it in the little community theater pamphlet. So I was super proud of that because it was funny and it made me happy. But also, like, the only way I got paid for that gig is I asked if I could have the motors and stuff afterwards, so I could not build a CNC machine like 10 years later, because some projects just don't happen. So we're going to talk about the most basic thing about time. What is a second? And it's the amount of time that elapses during 9,192,631,770 cycles of the radiation produced by the transition between two levels of the cesium-133 atom. So we have this thing with units where we actually like to redefine them in more scientific terms after we came up with what the original version was. So like we had seconds and stuff before, but somebody in some EU country probably said, oh no, that's not good enough. So they had to define it based on an arbitrary numbers of cycles of cesium, and like that number, which isn't really good for the song in Rent, by the way. I like workshopped this, and it didn't exactly have the right ring to it. So, you know, how do you measure the days of a year? So we're going to skip over a lot of the more analog timekeeping methods, but we're going to talk about a couple of them. We're measuring oscillations that have a known period, and the most common thing is your pendulum clock, or in this case, the cat pendulum clock, where the tail moves back and forth. And that is adjusting springs and escapements and clockwork elements that cause the hands to move in a very regular and predictable manner. But after some time, you have to put energy back into your clock by winding it up, moving the pendulum, refilling the water. There were many clever ways of doing clocks. The most clever, I think, and this is my ADHD moment number one, is the pneumatic distribution of time, which this graphic that I found on this website actually spelled out in all caps. And how do you keep mechanical clocks in sync with pneumatic genlock? I'm going to trademark that. So they did this in the city of Paris. They built these clocks that were mechanical in nature, but also hooked into this air system that they ran through the streets and sewers of Paris. And the left part of these clocks work absolutely normally. They had all the mechanics and springs and weights that would cause them to keep time. But one part of the clock, that was the mother clock in French, they didn't like to use master or slave either. That was an English term, and we're still trying to get away from that. So they beat me to naming the master clock the mommy-dommy clock. But they had the mother and daughter clocks. These bellows would compress and send a pulse of air every minute down to the other clocks in the system. And the biggest deployment of this was a citywide network in Paris, where they started with 14 and 33 clocks in municipal buildings. There's one like on the streets of Paris there in 1881. And they had this diagram explaining how it worked. And it was pretty interesting to me because they referred to the mechanical clock part as the ordinary clock, and that's what we have in our SMPTE devices. The term ordinary clock is for any device that just keeps time. And I thought it was really funny that they used the same terminology for it. And then all the plumbing on the right-hand part is the air distributing valve that allows the clock to either kick other clocks every minute or be kicked every minute to keep them in sync. So, oops, that was supposed to animate on. So they did pneumatic time at scale. So there's your AWS EU West 3 region in 1881 in the data center, where they had multiple redundant copies of all the timekeeping equipment in order to keep all this stuff working reliably. So they had up to 70 to 800 clocks at one point, and the whole reliability system was taken pretty seriously with things duplicated and quadruplicated. So you've got your red and blue networks. They were doing that in 1881, well before Cisco or whoever wants to take credit for that one came up with that terminology. And I think that one of the main reasons is that they had a pressure regulation problem. The bellows and all the clocks around the city would explode, and that would startle people. So I couldn't find an instance of that actually happening, but the author of the website that I'll link to at the end of the presentation about this referenced the clocks going pop, which was the guy's name. And I think that pun he probably didn't intend, but the author of the website definitely did. So you can see in this time data center picture in the left, there's actually a second one of those regulator cabinets behind it. So they were really serious about their availability zone. They had actually multiple facilities that would distribute this. So it was a lot more like the cloud than we might want to think it was. So moving into the electricity world, the first electrical clocks used this property of crystals known as piezoelectricity. It's a very simple circuit thing with a very carefully shaved off piece of quartz crystal. They're shaving them in the factory to tune them to oscillate at the correct frequency. And it basically is like a tuning fork. But the way these oscillators work is when they are hit, they generate a pulse of electricity. But if you also send a pulse of electricity into them, they will vibrate at a resonant frequency. So that is the basis for how pretty much most computer equipment actually keeps time. There's crystals everywhere on your circuit boards, in computers, in motherboards, in phones, in watches. There's newer, fancier crystals that have better properties than this giant one in this image. But like when designing an electrical circuit, it's not uncommon, like, I don't know, this board has like 3 or 4 crystal oscillators on it. And it just, that's what it needs. Different things keeping time at different frequencies for different reasons. So how do you measure the stability of this crystal is the first thing you've got to figure out. And the unit that came out for that is parts per million. And a watch crystal, like in a typical analog watch, has a stability of 20 parts per million at 39 degrees C. And when I read that, I was like, okay, temperature, parts per million, what are we talking about here? And what that actually means is if we take a 24-hour period of time, we've got 60 seconds in a minute, 60 minutes in an hour, and 24 hours in a day, and that's 86,400 seconds. And a 20 part per million error means that the error accumulation will be 20 over a million, and that's 0.00002. It seems like a very small number, but if you multiply that by the number of seconds in a day, you end up with an error rate of 1.728 seconds per day. So like on a wristwatch, that's probably not the end of the world, as long as you set it every day. Otherwise, you'll quickly be off. But if your computer got off by a second every day, and you left it on all the time, you wouldn't really know what time it is after about a week. So they came up with better crystal oscillators. Because they're very influenced by temperature, because of the vibrations and the mechanicalness of them, they came up with oven-controlled crystal oscillators, OCXO or TCXO, or common abbreviations for those. And they put the crystal in like a resistive heating element, and they're able to keep that crystal at its ideal range. The crystal on this circuit board is a 0.5 part per billion oven-controlled crystal oscillator. But it's just a tiny little chip. It's not like there's a microwave there with a bunch of buttons. It is as simple as any of the other crystals. It just costs like $80 instead of 12 cents. So like you can pay for how much accuracy you want. That's what's great about all the electronics stuff these days. And the spicy crystal oscillators are a part per billion. So going through the same math, you lose 1 second after 32.4 years. But scientists, being scientists, were preoccupied with whether they could. They didn't stop to think if they should build more accurate clocks, and they have developed the spiciest clocks of all time, and that's measured in parts per trillion. So the basic premise of atomic clocks is that they microwave cesium and measure the vibrations. It's not really a microwave. It is really cesium, and I don't think they're measuring the vibrations. I think they're looking at the oscillations. But top-of-the-line cesium fountain clocks can keep time up to 1.001 parts per trillion, and at that rate, it loses 1 second over 32 million years. So that's pretty good. We'll go with that. We're comparing everything into seconds, so all of a sudden, like, that second starts to mean a lot less. So we need some new units. We can come up with milliseconds, which are 1,000 times smaller than a second. We can come up with microseconds, a millionth of a second, so it's 1,000 times smaller than a millisecond, but we need to go deeper. What if we went 1,000 times smaller than a microsecond? You would get nanos, as the kids call them. A nanosecond is 1,000 times smaller than a microsecond. It is a billionth of a second. And this is a really, really difficult number to comprehend. But you could think of it as the distance that light or electricity travels in, 1 nanosecond is the amount of time it takes light or electricity to travel a foot. So we will let Admiral Grace Hopper explain this to us because she does a much better job than I can.
Now, I know nothing about computers.
She was on some talk show with this guy.
They've called you...
Not everything, all I can.
Yeah. But is there anybody who would know more?
Oh, I expect some of these good youngsters coming along know more.
But you're known as the queen of software. Is that right?
She invented like the
now, you know,
quite a bit about
that. That conjures an image of somebody who has a lot of Tupperware parties somehow.
Well, I could give you a nanosecond.
Okay, now I see. I don't even know what that is, Grace.
Well, you see, we started with milliseconds, thousandths of a second, and then we went to microseconds, millionths of a second, and now we talk about nanoseconds. That's a billionth of a second.
Mm-hmm. But
well, they told me billionth of a second, and I didn't know what on earth they were talking about.
Right.
It didn't make sense to me. So one day I called over to engineering and said, cut off a nanosecond, send it over to me. And so I've got a bundle of them here, and you can pick your color.
Oh, they come in colors. See, I didn't realize that nanoseconds now. In the old days, you only had your choice of white or gray, I think. Now, Grace, see, I understand that this is
we're going to also pass out nanoseconds.
That is the maximum distance that light or electricity can travel in a billionth of a second.
No faster, no farther.
And, when an admiral asks you why it takes so damn long to send a message by a satellite, you point out to him that between here and the satellite there are a very large number of nanoseconds.
I guess so. All right, I'll tell you what, we have to pause here, Grace. We'll be right back.
So there you go. The sort of the universal speed limit for communications, a foot of wire that. I'm sorry, Connor's going to be finding these forever. Please try to you can make them into friendship bracelets. It's a wonderful giveaway, I promise. So I was like, okay, what would it take to get nanosecond precision at home? And I found a cesium reference clock on eBay for just under $5,000. It's pretty big. It has a major alarm button on it, which is kind of scary. The description said not much used, and So I'm sure they claim it was the backup. It's never been turned on. It was not used for mining. So we'll throw that on the Christmas list. Definitely want a cesium frequency reference. Don't know what I would do with it. But what time is it? Time is a flat circle, the conspiracy. So we talked about stability but not accuracy. So we know how clocks drift, but how do we determine what time it is? And a bunch of international standards came about to define this. But of course, in the beginning, everybody just decided on their own time. And in order to facilitate commerce, they decided that the prime meridian, the line passing through Greenwich, England, because of colonialism, was where they were going to say zero time was, and everybody was just going to be offset from that. So that's probably not the best choice they could have made, but that's definitely the choice they made, and we're stuck with it. So in 1960, we started coordinating time between countries. And the result of that was UTC. They averaged the times of several hundred atomic clocks all around the world. Most days, I love the weasel words and all these things, are 86,400 seconds long. Every once in a while, they add a leap second to keep the UTC in line with the rotation of the Earth. Atomic time doesn't do that. So the first leap second happened in 1972, and there have been 27 in total. The statement on average a leap second occurs every 21 months, but the last one was in 2016, so we're overdue. I feel I Googled the next possible date is December 31, 25th. However, the Earth's rotation has been relatively fast lately. And it's just what kind of statement is that? Is somebody actually measuring this? So they could add a leap second at any moment based on information that I don't know how they're measuring it. So we're in the best timeline, obviously. So yeah, UTC 0 is still Greenwich Mean Time. Thank you, big time. So how do we distribute time? Obviously, we put atomic clocks in space. That was the most convenient way we could come up with, and it is actually pretty convenient. So the government built this for us. The GPS fleet of these of these totally normal-looking satellites that definitely aren't from a Steven Seagal movie. By computing the time offset of at least 4 different satellites with their known position, GPS receivers on the ground can determine both their position with a surprising degree of accuracy, but it actually works by collecting these highly accurate timestamps. So you're you're paying for position, but you're getting time for free. So that's one of the benefits of using GPS as a time source. And a side effect of this is because the atomic time in the satellites is used you get it for free. But like, how accurate is it? And it turns out that like a really good GPS oscillator can resolve time to about 1 part per trillion. So that's that 32 million years you lose a second number. So like in number 1, like the best thing you can have is like the cesium microwave on eBay. And number 2, you can have a GPS receiver, which is in like every phone, car, and piece of personal electronics. Hello? GPS, everybody was really afraid of it in the beginning. So they decided to come up with this scrambling method so that the GPS timestamps weren't totally accurate, so that the baddies couldn't figure out how to locate our stuff by listening in on it. But it turned out if you had like 3 or 4 ground receivers and you just averaged them, you could eventually figure out what all that scrambling was and remove it. So there was effectively no real reason to continue scrambling GPS. So on May 1st, 2000, Clinton ordered this selective availability feature turned off. And this graph shows the relative error rate of GPS the moment they flipped the switch, disabling that. And newer satellites, allegedly, don't include that technology to scramble the time anyway. It's just a normal thing now, because every nation has their own global positioning, global navigation system. There's Baidu in China, there's GLONASS in Russian, and a lot of the chips, like the GPS chip on this board, it speaks to all of those constellations. It doesn't really matter. Japan also has an indoor GPS system that is based on satellites, but for navigating in shopping malls. I learned that while reading through the documentation for that chip. It's like a certain frequency you can use, and you can find where you are inside a mall. Cool. So yeah, what on earth does this have to do with live pixels? I feel like I got kind of derailed. And we're trying to figure out how to keep our stuff in time. And we do this with Genlock. And this goes back to the analog video days, where in order to switch cameras, the cameras had to be in time with one another. And the reason was switchers back in the day were these really dumb devices that would just cut between signals. So if you accidentally cut a signal off in the middle of it, you'd have half of one picture and half of the other picture. And that's how you prove that the moon landing was fake, because somebody cut something wrong. No, like people look for like signs of aliens because things were getting cut improperly in analog television. So they would buffer from the top of the frame so that the cuts happen at the right time. So they came up with Genlock. It sends a blank black frame of video to every device, and then the incoming signal is looked at, and the device figures out when it's going to start its first line of video. It's generated 525 times per frame, once for each line of the analog TV standard at 59.94 frames per field, because we had interlace back then, so there was really only 29.97 times per second. And it's known as black and burst, or black burst as the kids call it, because there's the black portion of the signal and the wavy part is the color burst. Most devices didn't actually use the color burst signal, and they definitely don't nowadays. It's just kind of a vestigial thing left over from the good old days. With HD in 1998, they came out with tri-level sync. And this is the Bateman-Cell-rotational compatible color rant. Why are the frame rates 29.97 and 59.94? When they invented color television, they decided to hide the color data in each line of signal, such that most black and white TVs wouldn't even notice it because they weren't precise enough. In order to make this work, they needed to change the refresh rate slightly to make the math work out. So again, in such a way that non-color sets weren't any wiser. So compatible color, which is what they called this, was a triumph of engineering, probably found out by like the smartest engineers at RCA at the time, a General Electric company now. And it's a burden on video engineers ever since. So you look on Reddit for people complaining, why is my gaming monitor doing 119.88? I want 120 hertz. It's literally unplayable. We still have interlaced and fractional frame rate in high frame rate gaming monitors, because we're unable to get away from this standard from 1953. So with tri-level sync, it has 3 voltage states, low, middle, and high. So it goes up, it goes down, and it goes back up. This thing's supposed to generate tri-level sync, but because I made it wrong, it goes up, and it goes down, and it goes, because the third level didn't really work. So that's on my to-do list. So tri-level sync has a wide variety of frame rates, including even 30 and 60. So that'll make us computer people happy. So you can actually set your clock to 60.000 hertz. Old Genlock didn't have that. It was always 5994. And it's still distributed using analog DAs. So you get a nice BNC cable plugged into your computer. None of these signals include any concept of date or time. They're just oscillating reference signals. You're just trying to figure out when something starts. They don't actually tell you when it is. So to do Genlock in computers, you need one of two, just one card, because AMD discontinued this, so good luck. And during the pandemic, the QuadroSync cards were basically impossible to get. So like you could buy like HP branded ones on eBay for like $3,000. But anyway, this allows us to connect our most expensive professional GPUs to a blank television signal from the 50s. So what did we do wrong? It's interesting, actually. Intel has an open source GitHub library for doing software Genlock utilizing PTP and Linux. I have yet to have time to recompile the Linux kernel to make this work. And I also don't have an Intel GPU. But this is really interesting because it adjusts the frequency of the GPU based on PTP. And this sounds like a really awesome solution to keeping computers in sync that doesn't involve analog television signals. So, fun facts about computers and time. Turns out computers are actually terrible at keeping time. And the whole temperature and clock stability thing is a real mess. Computers are also doing a lot and can't focus on keeping time, particularly Windows, although I do hear it's getting better. Most users don't need their computer to have really good time. So they use cheap crystal oscillators because computers have to be cheaper because that's how you get Dell. Most computer clocks, if uncorrected, would drift at least a second a day. And that was like totally cool because all computers were doing was authenticating against Active Directory somewhere at work. And as long as you were within like 5 minutes, you're probably fine. But commerce and video games, now there's reasons for computers to actually need tighter synchronization timing. So we'll have to solve that. And the way computers keep track of time, they count the number of ticks since the epoch. The epoch is Thursday, January 1st, 1970. I know it's a Thursday because I once accidentally set up an NTP server that was misconfigured at home, and all my Windows machines in the taskbar said Thursday, January 1st, 00. And the Mac didn't care, but for some reason my PCs all happily believed it was the 70s. So Disco isn't dead. The default timing resolution on computer clocks varies very considerably. One of the most accurate computer clocks that existed for a while was the Apple Watch, incidentally, because they used a very special kind of MEMS gyroscope monitor in it to do the vibrations for the crystal. Turns out it also doesn't work when there's helium, so somebody had a leak in their MRI machine, and everybody's iPhones and Apple Watches went crazy because the crystal stopped vibrating under helium. A weird side effect of somebody's otherwise very good choice. If you put it in a bag with regular air, it would eventually come back to life, just like putting your phone in rice after getting it wet. But people were really confused. It's like, why does the helium affect the phone? And it's crystal. So if atomic clocks are so good, why not just put the atomic clock in the computer? You absolutely can. You can buy the OCP time card from these people at TimeBeat. They had a Valentine's Day sale last week. They're made in Britain. Honestly, like TimeBeat, if you want to play with this stuff, I'll link to them later. They're a great place to buy Grandmaster clocks, little boards that you can plug into Raspberry Pis to do time stuff. They're a wonderful company, and their engineers for support were really helpful to me when I was working on portions of a different presentation and found some bugs in the PTP software they had. So I definitely want one of their atomic clock cards to go with my cesium reference clock. And so if you don't buy from them, Jason from TimeBeat's going to slide into your email. This Valentine's Day, we're spreading the love with an exclusive offer. I think they could find a better mascot. So I went and did find a better mascot. Her name is Oro Crony. She's a VTuber. She has 1.03 million followers on YouTube. she mostly plays Minecraft and other games, but sometimes she just like is a regular like just chatting streamer. She's designed around being a clock, some kind of goddess of time. She also has a Neko form, like everyone does. And also, canonically, she has a helicopter form where she can use her, I don't know. It's very strange, but it's not the strangest thing I read this week. Yeah, so also, she got hacked, and apparently somebody started a crypto coin after her. Then there's all these like relatively serious like crypto podcast YouTube videos discussing the situation. It spawned memes about the crony coin going to the. I've had enough internet. Oh, just kidding. Anyway, so how do computers actually keep? Sorry, video people. NTP. This is how most computers that are not very fancy adjust their clocks. It uses a series of stratum to classify what the best clock is. A stratum 0 clock is an atomic clock or a GPS. It's not on the network, it's only a reference. So your time server that is connected to the internet is a stratum 1 time server. So that's like, I like to imagine it in some very fancy government facility with like multiple locked doors, but no, they're all over the place and anybody can run one. And there's actually like communities of people who run NTP servers for fun. And you can have many, many different NTP servers to communicate to make sure you're getting valid time. So any computer that gets time from a stratum 1 clock is a stratum 2 clock. Any computer that gets time from a stratum 2 clock is a stratum 3 clock, and so on and so forth. Each step you get away from the GPS clock, you're theoretically losing accuracy. So NTP is not actually the authoritative time in the system. It's actually used to discipline the system clock. And it does this by making very small corrections to the frequency over time to prevent wild swings that would cause real problems. So this cat is disciplining the clock so that its owner doesn't realize that it's not dinner time. So the cat thinks that if he adjusts the hands of the clock slowly enough, the owner will look up and say, oh, it's dinner time, and then feed him. And then ideally, if he does it slowly enough again, he'll get fed again. But, you know. NTP is accurate within 1 millisecond, and that's a really accurate way of how clock disciplining works, just a little bit more analog than usual. So for basic business needs, NTP is good enough. You know, nobody needs more than a millisecond. And most computers don't run a real-time operating system, so they wouldn't even know that they weren't dealing with more precise elements of time. So NTP works by just asking the server, hey, what time is it? And the server says, hey, it's Wednesday. And probably what time it is within a millisecond. But if you have a Stratum 1 server on your local network, like if you're at Amazon and like they have a GPS antenna on the roof, you're getting pretty good time. And for anything that you're doing database-wise, unless you're doing consistency across multiple databases, which is what AWS will actually sell you PTP for nowadays, you're probably fine with regular old GPS time. But let's just go better. We need more. PTP. We're halfway through the presentation, and I've mentioned PTP for the first time. Here we go. It's used in financial trading, telecommunications, oil and gas, drilling for some reason, scientific measurement, and broadcast. We're probably like the little like asterisk down there. Oh, also broadcast uses it. It defines an architecture where devices synchronize their clock by taking into account the delays inside the computer, as well as the delays transmitting the network. When it's set up correctly, PTP is able to distribute time as accurately as being connected directly to GPS, so somewhere in the part per trillion range. It can run in software-only mode, but the real benefit of PTP is the fact that every part of the network equipment, like they were showing earlier with the Mac and the Phi, is taking into account the timestamp when the packet enters and leaves the chip and is paying attention to that information to make sure it's being counted. How does PTP? PTP sends synchronization packets very much like NTP on the network, but they're a lot more complicated. So in this example, we have our clock and we have our computer. And our computer doesn't know it yet, but it's off by 100 seconds. So we're going to start sending these PTP packets back and forth, and we're going to collect a whole bunch of data in these packets, and then the computer is going to figure out its life and its choices. So the clock sends out the timestamp saying, hey, it's 0000. And we're going to say it takes 5 to get across the network. These are totally arbitrary numbers with no units because it makes the math look easy. And I hate math. I hate when people put up formulas, like I'm trying to explain this as best as I can. So the computer receives that timestamp, and it's going to write down that timestamp as T2. Say, hey, I got your T1 at 0105. Again, it's 0105, not 05, because it's off by 100 seconds. It just doesn't know it. Then it thinks about it for a little while. There's always some processing delay. It writes a timestamp 3, says, OK, I'm going to send you a new message at 0107. It's going to send that back out the network. It's once again going to incur a delay of 5, because this is a symmetrical delay network, which is one of the things that PTP kind of requires. And then the clock at the other end receives that packet, stamps it again, and says, I received your message containing T2 and T3 at 0012. I'm now going to send this back to you as timestamp 4. Sends it back, incurs a delay of 5. So at this point, the computer that's trying to figure out what time it is able to calculate two things. It's able to calculate the delay of the network. This is known as the mean path delay. And by following that simple formula of T2 minus T1 plus T4 minus T3 over 2, it averages out the error and figures out that the network delay must be 5. The other thing it's able to determine is the offset. Just how wrong is its clock? By subtracting the numbers and averaging them slightly differently, it finds out that the offset is 100. So it's able to discipline its clock so that it is closer to the time originally sent to it from the clock. Now, in a proper PTP network, we're doing this up to 8 times per second. Usually, like the standard I've seen in SMPTE is 4 times per second, is how frequently it's exchanging these messages. So like all the devices that are trying to synchronize time are all constantly yapping at the GM clock, trying to figure this out, and everybody's doing calculations constantly. This is why certain switches don't actually support being a grandmaster, because as the folks from Netgear pointed out, like there is like processing power related to doing this calculation. So inside every 3 PTP system, there are 3 clocks, not 3 wolves. The system clock, or tick, which is what time the program thinks it is. The real-time, or battery-backed clock, which allows the computer to remember what time it is even when it's been turned off. It's a low-power, relatively low-accuracy crystal that's ticking away even when your phone or computer is off, just depleting your battery, which is why if your motherboard battery is dead, your computer will wake up on January 1st, 1970. And then there's, in PTP systems, the PHC, the PTP hardware clock, and that syncs to the network. So what you actually have to do to get your clock to show the right time is you need to sync your physical clock to your system clock, and that's the Linux command pht2sys. And once again, it's like the cat sitting there moving the hands of the clock to adjust the time in the upper right of the Linux taskbar, at least on Ubuntu. So lots of confusing terms. Grandmaster clock. This is the big boss. This is the one that is determining what time it is. It's chosen by an algorithm, which is we very much like in 2025. The algorithm rules all. There's the leader, or the Dami-Mami clock, as I like to call it, because it's very consensual and everybody's on board. We're not doing master and slave anymore. It's 2025. We don't have that. We'll go with what the French did. Any clock that is the time source for any other device, and it doesn't have to be the whole device. A single port can be in leader mode or in follower mode. Oh, follower is the other kind of clock. It's a clock that is synchronized to another clock. Any port on a PTP-aware device can be in that mode as well. An ordinary clock, just like in the French pneumatic clocks, the ordinary clock is a device that is PTP-aware but doesn't act as a source of time. It just needs to know what time it is. These are your clients, your timing users. Then there's a boundary/border clock, and that's a switch that has multiple ports that can be in a leader or a follower role. And in that leader or follower role, the switch is actually computing its own distance between its leader and then substituting itself in as the new leader for the clocks below it. So if you've got 50 clocks if you've got like 400 clocks in your system, if you had 400 clocks yapping at your GM clock, it would probably explode. But if you put a boundary clock in between, you'd have 50 clocks going to each one, and then only 4 going up to the grandmaster clock. So it's really about saving performance, not network traffic as much, because 4 times a second doing all these calculations. Not good. Transparent clock is it's similar in concept to the boundary clock, but it is passing all the messages through it to the GM clock. So it doesn't solve the just chatting problem. Instead, it does provide for accurate PTP time because it is measuring the time in and out of its own ports. It's just adding that onto the existing PTP packets so that the calculations are accurate. We'll play with that in the demo. So the structure of PTP. This was the boundary clock we were talking about. You can see that one of the ports on the switch is a follower, the rest are leader ports, then all the devices at the bottom are followers. It's very similar to how a video DA works, where you have Genlock coming out of one of these clocks and a legacy device can take Genlock in from it. So Genlock can be derived from PTP, but PTP shouldn't be derived from Genlock. It's because PTP is epoch aware. PTP knows what time it is. Genlock only knows in what phase of the Genlock signal it is. So if you need time and date, PTP includes that as well. Whereas the phase is deterministic. It's determined from that moment in time in January 1st, 1970, where they turned on where they started counting from. They didn't actually turn on the first PTP clock in January of 1970, unless they had it in some secret government lab somewhere. Anyway, this is great for the broadcast trucks because all the trucks don't have to plug into the same source of time. They just look at the sky because they're outdoors, because they're trucks, and they use GPS time. Most of us live productions, we are considered what Verizon refers to as time islands. As long as all of our devices think it's the same time, we're good. We don't actually care that it's Wednesday or Thursday or January 1st or February 30th. Make up a date. We just need our stuff to have the same frequency reference. And it helps because we're indoors, so every time I've tried to demonstrate a GPS clock, it always blows up because there's roofs. So yeah, don't sync your PTP clock to house Genlock because Genlock doesn't know what time it is. Now we're going to talk about the best master clock algorithm. This is how leaders are born and how you figure out which clock on your network is the authoritative source of time. So the best mommy clock algorithm determines from a set of parameters, some of which are user configurable, others are not supposed to be user configurable, but are also user configurable in most systems. And they're evaluated in this very strict top-down order so that as an engineer, you can look at how things are set up and understand what's going to happen when things go wrong. Because the whole point of this is making this switchover deterministic and controllable, because if it weren't, it would be chaos, and that doesn't always work well. So they send these values out in PTP announce messages, like was mentioned earlier, and listening devices determine whether they want to be leaders or followers based on if they see a better clock or not. It's kind of like some sort of like Instagram influencer thing, but for clocks. So the first parameter is the PTP domain. It's a number from 0 to 127. And clocks will never select a grandmaster outside their domain. Basically, this is just, you could have multiple studios on the same network. I don't know why you would necessarily do that, but they could have different time domains. The next one, priority, 0 through 127. It's a user-selectable, lowest number always wins. And this is how you kind of determine which clocks are going to be leaders in a normal operation. So you pick relatively low numbers, but try not to do 0 because then it's just always going to take over. And you can have multiple clocks with the same number, and they'll fall over to figuring out what the best clock is based on clock class. And this is a non-user selectable, technically, lower indicating a better source of time, and they determined that some of these numbers have special meanings. Clock class 6 means your GPS lock, this is where you want to be. Clock class 7, the GPS has been covered by clouds, but it's within spec if it has an oscillator. So it'll hold on to clock class 7 for a little while until it determines that its oscillator is out of spec. Clock class 220 is locked to house sync. So the phase is good, but the epoch data is probably not great. And then there's class 248, which it's locked to its internal oscillator, and it really doesn't know what time it is. It's just trying to hold on for dear life. The last number is priority 2, and that's kind of like the tiebreaker. So if all your things are the same, you're getting GPS, and your 2 clocks, whichever, you want to set one of these lower than the other so that you know which of your clocks is in time. So you know which of your clocks is actually the one in charge. Because if you set these the same, The tiebreaker is the MAC address. And I bet most people don't know the MAC addresses of their clocks, or to even look at a MAC address and quickly determine which one's lower than another. So you don't want this to happen. Always priority 2 differently so that the lowest one is the one you want to take over. So here's an example of how this is calculated. These 2 clocks have domain 127. Their priority 1s are set to 10. The one on the left has GPS lock, so it's class 6. The one on the right has lost its GPS, so it's class 7. So the one that's going to take over is the left one because it has a better clock class. Here's another example. Same thing, but somebody has set the priority 1 on the right clock to 5. That means it wins every time, even though it doesn't have GPS. You don't want this. Because really, you want the one with GPS to be your source of time. So I would say that this one is misconfigured. Quiz time. All right, it's your turn. Determine who will be elected the GM via the BMCA.
Choose your fighter.
Any guesses? Yep, number 2. You're right. Because the priority 1 is lower.
This game's winner is...
Okay.
Choose your...
Yep. Yep, you got it. Because the clock class is lower, but the P1's matched, and the P2s don't even come into it.
This game's winner is...
All right, one more.
Choose your fighter.
No, it's a trick question. The domains were different. So these clocks are both leaders in their own little world. So security, we're going to kind of blow through this because I will say that most people in our world don't think about security enough. What if somebody just plugs in some random Raspberry Pi that's pretending to be a GM clock that has its clock class set to 2, and its P1 and P2 set to like meme numbers, and the date set to January 1st, 1970 at 4:20 p.m. It's got cows on the circuit board. So the truth is, if you don't do anything, you can easily turn any Linux system into a priority 1 GM clock, and it'll just happily do that. And the rest of your devices will just happily take over to that. The way that by a couple ways, you don't enable PTP on ports where you don't need it, but also in production networks, there's a concept called the AMT, the Acceptable MOMI table, and that's basically a list of clocks that you're allowed to listen to. And you put your equipment in there, and that way somebody with their own MAC address or their own clock ID won't actually win that election and take over. PTP 2.1 also adds some security features. I don't think anybody actually uses that. I'm not really sure what they are, but I'm sure it's great. We already talked about boundary clocks, so I think this was talking about what happens if everybody at the bottom's yap maxing at the Grandmaster clock and it explodes. So now, I wanted to measure how accurate PTP was, so I just needed to go to the store and buy this really fancy, oh god, it costs $22,000. But some intern made this product video for this thing, and it has no business going as hard as it does. They got like the vibrating text, they've got like these like glamour shots of someone picking it up because the old ones were like the size of like 4RU. Anyway, I want this, and also all the licenses. You can fit so many licenses in this thing. So that wasn't going to work. So I built my own test equipment because that allows me to do it on the cheap and learn about how PTP works. I did this by watching a bunch of YouTube influencers who were building these systems at home. And I came up with these devices, which, in addition to being PTP-aware Raspberry Pi clocks, they have these fancy little LED displays that are a prototype for something else at work on them. We first deployed this in June for Infocom, and I have it in rainbow mode because it was Pride, but I'm just going to keep it at this point because I like it. The generator is the one that's in rainbow mode. The other features that these have is they have a pulse per second output, which is a very precise signal that I can measure with an oscilloscope. So I can actually prove more accurately than this last digit just how close to being in sync my clocks are. So they're both on, good. What I'm going to do is we're going to go into the demo portion of this, and we've got some terminals here that are pre-connected and hopefully legible. And all of the software I'm going to show you is just a bunch of commands that you can run in Linux. It's part of the Linux kernel. It comes with Raspberry Pi OS. This is free, open source software that you can use to screw around with PTP at home. The first thing about my GM clock here is because I've disabled any possible way of it knowing what time it actually is, and it doesn't have a GPS unit because we're indoors, and that always blows up on me. We're just going to manually set the time off my watch to be about 15:04, and now it should have changed. And now we're going to start this one in Grandmaster mode, or Mommy mode. And it's going to sit here. It's going to assume it's the Grandmaster role. And then remember the 2 clocks, 3 clocks, however many wolves it is today. We need to synchronize the PTP hardware clock to this arbitrary time that we've set. So we're going to run the PHT2sys command with a whole bunch of arguments that basically force it to lock. And it's going to take a few seconds, but it's going to synchronize the 2 internal clocks inside this device so that they're within a few hundred nanoseconds of one another. And then I'm going to turn it off because the process of running that process actually slows the whole CPU down and causes the time to be less accurate. So this clock is now in sync with itself, as strange as that seems. And now we want to look at our boundary clock here, which is this fs.com switch I have, which is the cheapest, lightest weight border clock, GM clock switch I can find on the internet. It has no redeeming features other than that. The web UI always logs me out, and there's no way to change that. But if you go under Advanced Configure and go to where is PTP mode, and go into PTP config. Actually, we'll go into status. We'll see that our slave has locked to the port. And that's because we turned on the GM clock, and it's showing us what the offset from the master is. If I put it in auto refresh, you'll see these numbers bounce around as it tries to get more accurate. And we'll look at this when it's disabled as well. But at this point, we have locked our clock in, and I just want to make sure that the ports are on. I left them on. So ports 1 and 2 are enabled for PTP boundary clock mode. And now, if I go back to my terminal, we're going to go into the other clock, and we're going to start its PTP process. So it's going to listen to those packets. It's going to detect a new foreign master, and it's going to start calibrating its clock internally to that. And you see these numbers here that are progressively getting smaller or sometimes negative and bigger. This is the clock slowly disciplining its way into being in sync with the other one. Now you'll notice that the time hasn't changed because we haven't actually synchronized the 2 clocks within the box yet. So I will go run the same PHT2sys command, which will update the display time on this unit slowly, of course, because we wouldn't want it to happen too suddenly. And we'll see after about 30 seconds that these should drift into sync with one another. We're still about 12,000, 21,000, 81,000. Oh, there, it's a little closer. This is based on a proportional integral derivative loop where a bunch of calculus is happening back and forth to kind of find the sweet spot for synchronization, adjusting the frequency. Oh, connection timed out. I'm guessing it doesn't actually say the time, does it? It does. Oh, it does. All right, fine. So it's happy. Now, it's impossible to tell how accurate this is by looking at the last digit because it's moving so quickly. And also, I can't actually update the LEDs that fast. So we go to our friend, the oscilloscope, and we look at these 2 lines, the blue line and the red line, which are kind of all over the place for a second because I think the trigger value is too high. You will set that lower. Come on. Well, when it is in sync, it's very close to being in sync with itself. It's showing the number of nanosecond drift between the 2 clocks. Did I not stop this? No, this is also showing the drift going through the boundary clock, which could be causing some problems as well. And my other demonstration is to show what happens when you turn it off. And when you put it in transparent clock mode, maybe if I just restart that, will that value stabilize? I think it's not measuring it correctly because it comes back to the same place, but the wave just disappears. It's supposed to stay on there pretty constantly. Yeah. Well, it's not reporting any loss here. It seems happy. I think maybe the scope is loose. I don't know. I jinxed it. So we're going to go into the switch, and we're going to disable PTP real quick. And we'll see that our subscriber timed out. We'll see that this has stopped receiving and has determined that its local clock is now the best master. And we'll see that this thing is still kind of all over the place, but it's kind of drifting further away when it does get a signal. Drifting back. Well, where's the signal? Now it's drifting back for a line and a half. And part of the reason it's happening slowly is there's some holdover happening in the boundary clock. So if I look at status, it'll probably say free running by. No, it says holdover. So the switch is attempting to use its internal oscillator to keep time. So this is one of the, I guess, benefits of the boundary clock, that a mistake happening upstream has less cataclysmic consequences because there's something that's kind of keeping time in the meantime. However, eventually the holdover will expire and the time will drift way out. So I have to zoom out here to find it. Now we're looking at half a microsecond. So what we're going to do is we're going to go back into PTP config mode. And we're going to go into transparent clock mode, and we're going to turn on transparent clock. We'll see that the follower clock has instantly started seeing values from its buddy, and that they're pretty consistently in the 2 to 4 nanosecond error range. And now it's just absolutely locked on. I zoomed in too far. But well, once again, it's lost its mind. But when these things are actually communicating and being in sync, they are perfectly locked in sync. So yeah, it's good. Why does any of this matter? PTP is the basis for SIMD 2110. 12G SDI sucks. Take it from me. I ran a lot of cable around a building. It never worked right. 24 gig SDI. Oh, somebody actually specified that. SIMD ST2083. It has 2 wires. People are also talking about 48 gig SDI. It has 4 cables. They're absolutely crazy. There's all these limitations of fixed frame rates. So like, you know, this is all the normal SIMD 2110 stuff. Having it as a standard could allow a more open, expandable software-defined processing thing. It's like RenderStream, but free and open and standards-based. Vendor-agnostic compositing increases creativity and teamwork. And there will be eventual down market into the creator space. It would be awesome if I could just like fire up FFmpeg on my laptop and receive and send SIMD 2110 streams someday. Like that's the world I want. I want this to be as easy as NDI. So maybe we have time for like one question. If somebody wants to hand out a microphone. Do I have the microphone? Oh, I did have the microphone. Happy to take questions. Sorry, I got a little behind.
Alex, maybe you know this too, or either one of you, but you mentioned that the ability to program intelligence into the switch that keeps track of the packet timestamp on the way in and the way out, the egress and the ingress, I remembered. What do you know? What is an oscillator clock inside of the switch, or
yeah,
yeah.
Yeah, absolutely. Just like you said, on all the motherboards, they have crystals on them. Yeah, in fact, we have M4300s, old M4300s. The reason we ran so quickly to replace them with the M4350s, and you know, COVID happened, the whole world stopped, right? So it's very difficult to ramp up an entire billion-dollar company to release a new product of 11 switches. But we had to, because the M4300s, some of them don't have chips that are capable of tracking time. And one of them is actually a twin ASIC, so it's actually 2 switches in one, 2 24 ports. So yeah, definitely crystal.
It's all about the crystals.
Hi, live stream question. Someone just wants to know the name of the application, the PTP application that you've got installed.
It's PTP4L. It's also known as Linux PTP. It comes, maybe you have to get it out of apt actually, but it's PTP4 Linux, the number.
Okay, I think he's on a Mac, so maybe.
Someday.
Okay, thank you.
No, I mean, unfortunately, those tools don't really exist on the Mac ecosystem. So I'm terminaled into Linux machines here. That's what I was running.
Okay. All right, thank you.
All right. Here's the rest of that video. This is my walkout music. We would have the moving light ballad do it something. This is a real product video. I wish I could make something like this. It's amazing. It's so good. And if you want to read more about the pneumatic time system or compatible color, there's some QR codes.
Thank you so much, Kohler.
And someday there will be a 3 o'clock moon search.
Okay. It was
check one.
Super fun, super educational.
Enjoyed it.
Yep. So we're going to keep it rolling. Next up is Daniel Warner from Megapixel. We're just going to give him a couple minutes to transition, but Megapixel is one of the partners of the event and has been doing a lot to help this technology make its way into the mainstream of our industry because people love LEDs and having reliable, highly functional processing to be able to send ST2110 signals to walls like we're doing here is obviously a critical part of the signal chain. So they've already done some massive projects, which I know he's going to feature, but I'm really excited to hear what he has to say. So everybody, Daniel Warner.
All right, can you hear me now? Not yet. All right, can you hear me now? So visual technology is rapidly evolving from the early days of LED video processing to the latest advances in video sound and cameras, everything is now becoming part of a network, as we've been learning about all day. So I'm going to discuss how some of these technologies are converging. And I'm going to present a case study of the Eurovision Song Contest 2024, which was the first ever 100 gig ST2110 live event broadcast. So about me, I come from a background in Hollywood and production roles and technical roles, focused in cinematography, and I got into LED video processing through ICVFX. Yeah. Megapixel, we have hundreds of patents. We've got 4 Emmy Awards, and we've been involved in many technology firsts over the last 20 plus years, starting with Raster Mapper, which was the first ever pixel mapping software, leading all the way to Helios, which is the first 8K web-based LED video processing. 2110. Yeah, so Eurovision planning starts 2 weeks after the previous year, and technical suppliers exist to aid in the production of the event and to allow the event to use new and cutting-edge technologies. This was the first time since the show in 2009 that was hosted in Russia, where a single supplier was used for lighting, sound, video, and broadcast equipment. Our relationship working with NEP was a key factor on this. This one? Okay. I'll change mics here. So we were onboarded as the official technical supplier and worked closely with Creative Technology to validate a system design and deploy it for production. The production itself wanted to benefit from reduced rack space, latency, and equipment rentals. The video system was drastically reduced in size thanks to not having to deal with HDMI to SDI conversion and routing. And Eurovision has been using more and more LED now for several years due to EU mandates requiring LED. So we've got some pain points. We'll identify some of those. We need to move tons of video data around. We've got 2 completely redundant systems. Very little time on site to troubleshoot if things don't work when they come out of the box. There's very tight on rehearsal time. Stage time is limited due to the number of acts for the show. All the usual complexity of baseband systems added in with routing, latency, and many points of failure. We're often at the mercy of other products, such as network switches, media servers. So we need to work closely with these other makers. Specifically, some of the limitations of baseband formats include bandwidth and cable limitations that restrict video quality at high resolutions. Cable length limitations for large venues can become challenging very quickly. Complex signal distribution requires multiple converters and splitters, limited scalability with more sources, and our workflows are becoming more and more demanding and non-standard as we go. So the advantages of ST2110 in production are design, programming, commissioning, maintenance, and operation are faster and easier. The consolidation of multiple streams over a single network reduces complexity. Minimal latency and robust redundancy give you the best performance and simplified infrastructure with reduced physical equipment and lower power consumption. So what you're seeing here is the entry from Sweden, which consisted of on-stage LED, which had to be brought on, tested, and ready to go in 45 seconds. They have a 45-second changeover time between each entry. These setups reflect the unique nature of each performance. So all this is taken into account when building the show system. So this is what Eurovision looks like when you're sitting in the audience. The back wall has 680 row black quartz tiles, and the floor is 540 black marble tiles. And the cubes, which move up and down, are row vanish. So this is a video of the floor, which is obviously LED. And this allows the team to do very fast changeovers because the floor becomes a field of cue markers, so they know where all the props and set pieces go for very fast changeovers. This is the view from the audience. So while there's a postcard setting running on the broadcast feed, the next stage is being set for a new act. The crew have 50 seconds to accomplish this. Making it very clean. So this is a bird's eye view of the Eurovision network. It's very detailed, so you might not be able to see all of that. But there's two systems, red and blue. Front of house can see and control both networks. The content creation suite is also connected to the network to push new content onto the servers during rehearsal. So the media servers are on a 25 gig network. There's also 100 and 200 gig parts of the system. The Helios was configured in seamless loop redundancy, which means the LED tiles are displaying data simultaneously from both the primary and the backup systems, and the tiles are intelligently deciding which Helios stream to take from. It takes the first packet that arrives. So you would never know if a system had a major failure. You could be looking at the LED and you'd never know that. So we had 10 media servers, 3 switches, 100 gig, 14 Helios, 45 downstream switches, 2 megapixel Omnis monitors, and we had a network bandwidth of 1.4 terabits. This is the network dashboard that shows all the Helios and switches with their status. So this is where you would look to check for any failovers because you wouldn't be able to tell if you were looking at the LED that there was a failure. This is the network bandwidth. We had pretty high throughput numbers. This is showing 1.35 terabits. And this is the media server dashboard. Again, so these dashboards are how you monitor your show. And I'm going to compare a traditional data path with what it looks like in 2110. So all along the signal chain, we've got copper cabling, protocols that are different with also physical connectors that are different. This all adds latency, cost, and potential points of failure. So if there's a failure with, say, the metadata, the tiles may not know what color space they're supposed to be set to, and your colors will be inaccurate. So you can manually override this, but we don't want to be doing that. We want metadata to be correct. So on a network data path with 2110, all these devices just plug into a network and become devices on a network. We're bringing all of these different signal paths into one central core, so any piece of equipment can get any piece of data it needs. It's worth noting that for Eurovision, the 100 gig switch is only a couple of rack units tall, whereas a comparable HDMI SDI unit, the infrastructure would be a lot larger. It would be entire racks larger than what we had. The video village was quite small on Eurovision, considering the size of the show. This is more of the network, but it's also impossible to read, so I'll skip over that. So the benefit of 100 gig native fiber input, we can take in native 8K sources. We can stitch 4 4K 60 rasters into a single 8K image. We can also do, obviously, as we all know, LED is always custom and bespoke, so we can do up to 32K panorama in 1 RU. This has all been pre-tested with Matrox, NVIDIA, Unreal Engine, and obviously PIXERA, as you can see behind me. So the benefits of 100 gig, reduced latency, fewer interconnects, more reliable metadata, robust IoT-centric monitoring, modular and flexible ingest, which I can tell you from personal experience is a huge, huge deal because we don't work in standards. We may use standards, but everything we do is so custom that being able to just bring all your pixels in giant buckets really makes life easy for everybody. So I'm going to talk about metadata. we've got a lot of systems, and they're all important, right? Not just LED, we've got pyro and fog, audio, rigging, cameras, servers, show communications, lighting. So here's an example of network benefits, the camera cutting process. So instead of cutting cameras manually on Eurovision, they use live edit over network. So they've got frame accurate shots, frame accurate edits being timed perfectly throughout the show. This is all pre-packaged. So they've got like single frame edits, really sometimes difficult to look at, perfectly timed with all the pyro and lighting, everything happening on stage. So here's an example of that. So imagine an entire show with all these crazy synchronized things going on. It's all handled over the network. So visual technology is rapidly evolving. It's important now more than ever that with today's workflows, we utilize infrastructure that enables creativity rather than stands in the way of it. Unfortunately, I was not personally at Eurovision, although we had some team members who were. So if you have questions, just let us know and we'll get you answers, but I can't answer questions about Eurovision. I wasn't there, but thanks. Yeah. Yeah.
I have a non-Eurovision question.
Yeah.
Do you see a world? Can you imagine a world in the future where the render engines and all that stuff are able to talk directly to the LED tiles because they've become higher resolution or higher color? Or do you see SMPTE 2110 as a possibility for that world where the tiles themselves become the processor and therefore any of them can get the data from anywhere they need to in this like super hyper redundant sort of cluster workload?
Yeah, I would say anything is possible. The tiles themselves are actually doing a lot of the processing already. So, and we are working very closely with Unreal Engine. So, I mean, it's just a matter of how badly do people need it, and we can develop it. Yeah.
Yeah, I had a question. So on the SMPTE model, Helios that you guys have that has that 100 gig link.
Yeah.
The timing has had an issue on that link specifically. Is that something that's coming in the future? Because we've had to connect it to different ports, like a 1 gig port for the timing, but then the SMPTE video is coming over the 100 gig link.
So yeah, we take PTP time in through the network port on Helios. That's the way the system's designed. I can't answer whether there's a plan to change that, but we're taking the video in over the 100 gig, and we're taking PTP in over a network port adjacent to the 100 gig port. Yeah.
In your hot failover topology, I think you guys had red into the primary processor and the blue network into the backup processor. I think since that project, you can now take the secondary feed over the same NIC, so like a purple type configuration. Is there best practice? I mean, are you still deploying it like you did at Eurovision, or have you modified that with the new feature?
I can't answer that. Yeah, I was not really involved in the show, and I can definitely get you an answer to that. I just don't have it for you right now.
Thanks, Daniel. Thank you very much, Daniel. So we'll take a quick, just 5-minute bio break, and then we'll get right into Keith Vidger from Panasonic's presentation. So we'll see you in 5.
Gotta put his, we're putting his presentation.
PowerPoint stuff.
Thumb drive is a foot length.
I have a.
Oh, nice.
All right, thanks everybody. We are back on. This is our last presentation of the day. We're really excited to have Keith Vidger from Panasonic Connect here. One thing that I just wanted to bring up that Kyle from Matrox really reminded me of is I don't think we've done a good job of really driving home the point that this whole thing is ST2110. So we've really put our money where our mouth is. The whole production system, the whole the Kairos is handling the feeds and routing everything. I know our production skills, we're a media server company, so we're trying our best on the production quality, but I think the technical back end is all ST2110, thanks to all of the manufacturers. So we really wanted to make the system fully ST2110 to be able to do the presentation. So happy to go more into detail on the signal diagram after Keith's discussion, which Kairos, we couldn't have done this without Kairos, absolutely, and all of their support. Panasonic has been fantastic helping us with the cameras and with the Kairos operation to make sure we have a really good live stream going out there. After Keith's presentation, we'll be here for about 20 minutes afterwards to answer any questions, but we do have some shooting that we need to do tonight while we have personnel and equipment here, so we'd appreciate not lingering too long. There is a brewery up the street called Santa Monica Brew Works where people are welcome to go. We'll show up there after a little bit if anybody wants. It's literally up the street, Santa Monica Brew Works. But that's the housekeeping. Without further ado, Keith from Panasonic. Thank you, Keith.
Thanks. It's always great to be a manufacturer at the end of the day and be told that, rather than stay and talk to Panasonic about those cool products, why don't you go to a bar? So
you could say 30 minutes, I said, 30 minutes.
So we'll move along. It's been great to work with our friends here. So the one thing, though, that it struck me as being interesting throughout the course of these fantastic presentations and all the cool information is that, of course, it's largely geared towards people that have a lot of experience in 2110. But what if here in our local audience or those out in streaming land are not super familiar with 2110? My presentation is kind of geared towards the idea of there's been lots of great detail, sometimes nth degree detail. I might even suggest, what if I just want to make a system work? What if I don't want to build my own Raspberry Pi clock off of parts from eBay to get my production on the air? Can I just buy commercial products? I don't know, maybe from a company like Panasonic and just put it together quickly, easily, and produce great television? So that's what I'm here to talk about, the simplicity of 2110 as opposed to the obscure, if you will. So let's go through a quick thing. But as so many people have said, when you look up things about 2110 online, you'll often find very confusing super technical kind of details and things like that, it's not easy to get a straight answer. So I wanted to start off with something just like that. Here is a fun concept about the technical nature of digital video. Now, at the risk of reading this, some of the words of which I might mispronounce and all that kind of stuff, it's a fairly intense concept about how digital video works. And you might think, this is a little too much for me. I don't know that this is really what I learn about when I simply want to put on my production, which might be corporate or house of worship or broadcast television or sports or all those things. I just want to think about creating cool content, not about this. So people would say, basically, let's stick with SDI. SDI is pretty cool. I know SDI. SDI is nice and simple. It's plug and play. Lots of cool benefits. I get it with 2110, but I think I might just stick with my SDI. And to that I would say, psych, because this is the SDI spec, not 2110. Has anybody who's ever used SDI thought about this as you're putting together your SDI systems? Yes. With one exception in the room. Huh. So, there is a need, of course, for the brightest amongst us, we'll say, to have this information in their heads. For the 99.9% of productions that go on the air or entertain people or how you drive your revenue as an industry, you probably aren't thinking about this. Still, important that it's there and all this sort of thing, but you don't have to think about this when you do SDI, and you don't have to think about the world's most complicated technology when you think about 2110. We tend to kind of go that way, and today I would sort of reinforce that you think about the world's most complex technology when you think about 2110, but it's not necessary. So again, my job, simplify the world of 2110, make you feel comfortable using it if you haven't already done so. And building on some of the cool slides that I saw not that long ago, some quick benefits about why 2110 exists as compared to traditional SDI, a fun little detail. I'll ask everybody but one in the audience, when did SDI first come out? What year? 1989. How many other production technologies are using today in what you produce that were invented in 1989? Not many, but the whole core of how you get signals around in the SDI world is that old. So it was, we'll say, due for a refresh. The overall technology in our business refreshes all the time. That's why we're not still using NTSC and things of that nature, or PAL if you're in Europe. So now we basically got the idea of a technology refresh to get our signals from point A to point B and everywhere in between, and 2110, we would suggest, is one of the great ways of doing that. So lots of great benefits in terms of why you can essentially get all kinds of cool benefits out of making the change, and of course the usual effort that goes into making any change. There's some downsides to it, learning about things, getting used to it, that sort of thing, but we would submit worth the effort because of all the benefits that you do get. So, not the least of which, bidirectional signal communication, the fact that your reference signal is embedded as part of the overall package that's going back and forth. We can think of it as independent streams that are cobbled together very elegantly, so we don't have to do a de-embedding, embedding, and things of that nature. Lots of great things that go into why 2110 is here. So now let's turn our attention to a practical system. So, comparing again SDI to 2110, this is the SDI, the old school way of doing things, or OG, I suppose, if we were to think of it that way. But we can think of it as being about as simple as could be. I'm going to connect a couple of cables from my two sources into the world's simplest video router here, and a couple of destinations. Super easy. I'll hook up my control panel, make my route, and before you know it, I'm making great video. Super easy. Couldn't be simpler. Love it. Why should we ever think about doing anything else? Well, let's now go to the world of 2110, and before we even start connecting cables, we can suggest you need to put in a few bits of information. Your stream IDs and addresses and things of that nature. Don't forget your port numbers in there. So lots of great information to essentially identify where your content is coming from. Not really something we think about in the SDI world. So once we've typed in this great information, both on the source side, your destination side, that sort of thing, now it's kind of business as usual. The actual type of connectivity, as we said before, is different, and not so much copper, even though that's possible in 2110, of course, but more we'll think of it as glass and fiber optics and things like that, and hook up our router control panel, and now we can go ahead and make our routes, not unlike what we did before. So you could certainly say, wow, thanks for making this 2110 system. Seems like I get everything I had with SDI, but I have to type in a ton of numbers. So not exactly all that much of a benefit, it seems like, but let's go back to the world of SDI. So we've got that same exact system we saw before, 2 sources, 2 destinations, everything's looking great. But what happens if I want to have my cameras in time? So of course I need black burst. Well, I was glossing over that part. Well, certainly you're going to have return video probably, and teleprompter, okay, yeah. So those are all separate signals, of course, and that sort of thing. Oh yeah, if you want to embed audio or de-embed audio, yeah, it's not really done in your router, so you're going to have to take that SDI signal out, go into a de-embedder, for example, and then take out your audio. I've been to some great TV stations across the country, gloriously huge router, 512 by 512, super nice, the height of elegance, the kind of cable management you would only dream of. And then there's about 40 inexpensive audio and de-embedders hanging off the back, in some cases dangling there. Like, not elegant. And you're relying on technology that, in comparison to your $1 million router, you're talking about a $100 converter. I don't know if that seems like it's kind of balanced and all that stuff, but ideally there'd be a better way to do that without having to take signals out and put them back in just to strip off audio or ancillary data. Okay, so here's another thing. Now we've got our signal connected from camera 2 to input number 6 on our router, as you might be able to see up there. And again, we're talking about, well, oh boy, maybe fewer buttons and larger would be better for me. Okay, so we've got our nice connection here. We're going to jump ahead to our audio de-embedding concept. Now we move our connection from input number 6 over to input number 5. So sorry, the PowerPoint is now fighting me. Apologies. Okay, so here's where we left off in our program. Now we have our output from camera 2 going to our input 6 on our router, and somebody, for whatever reason, misconnects that cable. So they take that cable that was going to put 6 on the router, they put it to 5, and as you might imagine, the next thing is going to happen, you no longer have anything going to that monitor. Seems like this shouldn't happen. Technically speaking, you shouldn't be doing this kind of thing, but it happens all the time. Constantly and forever, signals disappear when you expect them to be there because somebody pulled a connection, a patch probably, all that sort of thing, and it's not there anymore. The router doesn't know any better. The router says, hey, there was a signal there before, it's not there now. How about black? That seems like a good thing to put on the air. And so what's the router know about it? Nothing. Router takes what you give it and puts it somewhere. It doesn't know what the source is, doesn't know the actual original camera 2 in this case. How could it possibly know that? So it doesn't, and you end up with nothing. Again, happens an awful lot. Now, let's go back to our 2110 scenario. We talked before with ins and outs, but really, as we probably, most of this in this room know, they're duplex. So they're ins and outs. Every connector on a switch, for the most part, is again going to be an in and an out. So therefore, that concept before of having all kinds of things like reference and your return video and your teleprompter, that's all on the same cable. That one cable now connecting, in this case, your CCUs to my switch, the 2 cameras there, now is containing all that information. And of course, there's the audio there too. So we're going to put in our stream address and all that stuff for our audio. And now if I want to pull that off, no de-embedder is necessary. I just take audio off of whatever port of the switch I want to pull it off of. That can go into a mixer or any number of places. It can contain many streams of audio, that sort of thing. No de-embedding is the moral of the story. So because 2110 has information, video, audio, ancillary data as separate streams, you don't need to de-embed or embed for that matter. Okay. So now we've got some practical benefits. Fewer cables, number one. If you've got a bunch of cameras, having fewer cables for return video prompt or reference, PTP of course, that's a nice thing. And not having to worry about all that collection or fleet of low quality de-embedders dangling off at the back of your $1 million router, also a nice thing. But what about that situation where we have somebody mispatching our situation? So something from 6 to 5, the input from 6 now to input 5. Again, in the video world, you get nothing. But in the 2110 world, it goes and finds that stream. It's looking for, in this case, 239.20.12, and it goes and finds it. So while somebody may have temporarily disconnected, of course, you'll have nothing at that point, but a simple repatch means it will automatically find its way home to you at the switcher. So now we're basically talking about some really nice benefits. We don't have to go sifting through hundreds, maybe thousands of cables looking for where this mispatch happened. I don't have to think about that because it'll figure it out for me. Not unlike when you're at home and you disconnect your printer from port number 1 on your router to port number 2, it just comes up again. You have to do anything about it. It basically finds its way there because it has an address. So that little effort that I jokingly said before, you have to type in a bunch of numbers and, wow, thanks a lot for all that extra effort. There's a big payoff there because now it's able to essentially get you out of jail free when you do a mispatch or things like that, stuff that's not going to happen in the SDI world. Okay. So now, let's go for the answer, or the situation, I should say, where we've got everything kind of dialed in, it's looking good, all that stuff. This is obviously 2 cameras and 2 destinations, not exactly the world's most complex system. What if you had, though, a major system? What if you had a lot of things? And in particular, if you're going to have a major system, probably lots of cameras. So let's talk about cameras in particular. So this idea, though, of I'm going to have my video and my audio, and I'm going to have my return video and my reference and all that kind of stuff. I'm going to have all that together. Some people are like, ooh, that's a lot of eggs in one basket. I'm not entirely sure if that kind of suits my taste. I kind of prefer discrete streams. I can go troubleshoot one thing. Seems like it's a little too futuristic for me, a little too Futurama. I don't know if I really want to do that. To which I would say this concept of combining all these signals together, essentially for simplicity, longer cable runs, less expensive, better quality, all the things we mentioned only a few slides ago here about 2110, we've been doing that for a long time, about 25 years. Anybody know what technology we've been using for about 25 years to combine reference and prompter and return video and video and audio together to elegantly get from where the CCU is all the way out to where a camera is? Triax. Ah, hilarious. So Triax certainly is that idea. Not exactly uncompressed or for high quality in the HD world, and not exactly super long cable runs, but SMPTE hybrid fiber, of course. If anybody isn't familiar with that, I direct your attention to that camera. Panasonic camera, by the way, standing right over there on those sticks. The one that's right over there, there is a SMPTE hybrid fiber cable connecting it into the CCU. Just about anything you've watched on television, sports or news and all kinds of shows like that in the last quarter century basically has been because of SMPTE hybrid fiber. What is inside that SMPTE hybrid fiber cable? A couple of different fiber connections, not entirely unlike, in fact, basically identical to SMPTE 2110. So if you've got essentially these 2 cables, if you want to think of it that way, you can see them there. That essentially one is responsible for going one direction, one's responsible for going the other direction, all that sort of thing. Really, that's what 2110 is. So if there's some trepidation about using 2110 because it seems like a lot, I'm not sure if that technology is really proven, for about 25 years, every Super Bowl, every high-end sporting event, every big news show, everything for the most part in broadcast has been done using SMPTE hybrid fiber cables. So the technology itself, well proven, long established. There's almost no television without this. Now we're simply just putting in IP addresses to make it interchangeable. You know, if you plugged a Grass Valley CCU into a Panasonic camera or a Sony camera into a Ikegami CCU, it's not going to work. There's a data communication there that's only meant to be one manufacturer's product to the same manufacturer's product. But we want that in the 2110 world to be open, so anybody can use anything from anything. There again, the Joker is coming to tangent. So we want the idea of this ability to interconnect anything to anything, and that comes from putting in those addresses. You'll see that's a recurring theme in the 2110 world, if you're not already a super genius, when it comes to the technology, that the stream IDs and things like that provide a wealth of flexibility. Okay, so hybrid fiber cables and all that are great, but again, what if we took it up from, that's just one CCU and one camera, what about a big, giant installation? So there's a broadcaster in New York that does a couple of pro sports teams. They've got 4 switchers doing all kinds of shows out to the greater DC area, and each switcher has 128 inputs, and likewise, each 40 outputs. So add it all up, 672 signals. Now, when they were first considering using SDI to do the whole thing, how many SDI cables would they need to do those 672 signals? Not much math involved here because it's 672 SDI connections. So you're like, all right, let's go get 672 SDI cables. You're like, all right, You might know that if you were to look at Canary and the other great manufacturers of SDI cables, there's probably about 60 different cables to choose from, all based on length and how much data and things like that. Is not as super slam dunk as most people think of when it comes to the world of SDI, hence the 12G issues and things that some people have had befall them and all that. But the idea is, all right, so no big deal, but that doesn't even count the cameras and the other sources there, all the other destinations and things like that. You're talking about a ton of information. But we'll restrict our conversation now just to the idea of connecting your 4 switchers to the router. So besides these 672 cables, kind of expensive in the copper-based SDI world and labor-intensive, imagine labeling, booting, and crimping 672 different cables. That's a lot of effort and labor going into it. As a result, yeah, it'd be nice if there was a more elegant way. And once again, enter our friend 702110, because the exact same scenario with the same number of signals going back and forth requires, in this case, 4 cables per switcher. And again, super genius math here, 16 cables total. 672 cables and, 672 signals and just 16 cables. So, if you were them, thinking about engineering this huge big system and all that kind of stuff, far less expensive, far more elegant, far easier to maintain, far easier in just about every possible respect. 16 cables for 672 signals. So, the one-to-one relationship that we normally think of as being part and parcel for SDI, that's not part of 2110. You certainly could if you want to, but it's much more elegant, much more practical to use essentially the benefits of 2110. Because unlike SDI, where again it's one-to-one, you can gang up the data of all these different sources, destinations, and things of that nature, and put them onto a single cable. In this case, 4 cables per Kairos switcher. Kairos, as you've heard probably in most of the presentations today, and which is running not only the video wall behind me, but this projected output and the live streaming show. That's the switcher that they have, or 4 switchers in this particular case. So now we've got all of these signals going back and forth in the 2110 world, into and out of a Kairos. And here's the quick plug about some of the cool things about why Kairos is great, more than just working in the 2110 world. The most important of which, I know we had a lot of technical talk here and signals and things of that nature and everything, but most people purchase Kairos because of its creative capability. You know, if you don't have creative capability in a switcher, you really just have a router. So if you're going to get a switcher, ideally you'd have the most creative capability possible. Unlike most switchers would have so many MEs and so many keyers and things like that, there's no fixed limit to the number of MEs or keyers in Kairos. So the number one reason people buy it. But it also happens to be great at 2110 and working with all the different kinds of inputs and outputs besides 2110, NDI, SRT, all that kind of stuff, SDI of course, and driving video walls of unusual aspect ratio, all those great things. So lots of cool deals. But now, circling back to when we first started off. Let's go back to the idea of, again, we've got stream IDs for all of our things, the stream address, if you will, the exact scenarios we had before, except on the bottom, the 2 different destinations we had, those monitors, really now just a Kairos. So we're going to do the world's most simplistic switcher situation. Normally, if we've got 2 sources, our switcher needs 2 inputs. Again, pretty straightforward. If you have 20 sources, you need 20 inputs, 40 sources, 40 inputs, on it goes. But at some point, one of the big downsides of SDI is that you essentially have a fixed number of connectors. It's a one-to-one. And the moment you basically go and say, I need to get a ton more money in budget to be able to buy this big switcher, which I don't know, has 128 inputs, everything's great. I'll never need more than that. What happens one day later? I need 129 inputs. So, happens all the time, but there's nowhere to go. So you've maxed out the input count on your switcher or the output count, you're done. So, it'd be nice if there's some way around that, some, again, get out of jail free card to allow you to use additional inputs and things of that nature. But now, going back to, once again, the ever-present stream ID or address, if you will, of our 2 different cameras up there. You see one's the 21.1 and one's 21.2. Okay, so now we've got these 2 different addresses and all that. That one output going into Kairos, you see the camera 2 is hot or tallied on the air. But the idea is, you know, your router, or the 2110 switch in this case, again, emphasis on the word switch, is capable of instantaneously switching from one signal to another. So rather than have a dedicated and expensive input on your switcher, can't the switch just do that for you? Can't the switch make the switch, if you'll pardon the alliteration, I guess. All right, so the answer, of course, is yes. You can have your switcher, simply by pushing the camera 1 button on your control panel, call up the camera 1 stream ID. So instead of the other signal from camera 2 filling up that one connection between the switch and your switcher, I know there's a lot of switches in here, you have the ability now to have it switch within the switch itself. Yeah, we'll say transition within the switch itself to make it a little bit easier to understand. And so now if I go back, camera 2 is now back on the air, now camera 1's on the air, and back and forth I go. One input to the switcher, but we're able to put 2 different cameras, or 3, 4, 5, 10, 50, whatever, signals on the air, even though there's only one signal there. Now, obviously, this is the most boring show, and therefore an oversimplified example. But more than likely, you're going to have 60 inputs and a handful that you probably don't always put on the air. So maybe you're going to reserve 4 inputs for 25 different cameras, things of that nature that you use very, very rarely or sparingly. You don't have to burn an input just for some camera you might put on the air for 30 seconds during your 3-hour broadcast. But you don't want to not have that camera either. So this scenario, called smart routing, is a ability within cameras to utilize the very smart technology that exists within any 2110 switch. It will go out and find the IP that you have, because you see here at the keras level on the bottom, it's actually already typed in there. So by calling up camera 2, it knows to go to that, and in this case, going to, oops, one too many, going to camera 1, basically because it knows the address, it goes out and tells the switch, give me that. Over my 1 cable, in this case, go give me that signal. And again, usually magnified many, 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 many times. What's that movie from, by the way? Commandant Lassard from the Police Academy movies. Okay, we were doing trivia for movies earlier. So now we have the ability to address loads upon loads upon loads of sources without having a built-in connection on your switcher permanently there at great expense to access them. Now your switcher can reach out and tell the switch, in this case the 2110 switch, to give it what it wants, only when it needs it, and away it goes. I like to make the analogy of, you know, we all, I'm guessing, or at least some of us, most of us maybe, grew up in an area where you had cable TV, and you had so many channels on your cable television box, and you would go through and find your HBOs and Showtimes and CBSs and all those kinds of things. Basically, it was fine. But there's only so much bandwidth you can get down the cable into your home. So you're basically limited in terms of how many channels you could see, whether it be over the air transmission, whether it be on your cable box or satellite box, based on how much was coming in. Once again, kind of that one-to-one relationship. But now, almost nobody watches TV that way. What do you watch, basically? Streaming. How does streaming work? Well, when I'm not watching Netflix, I then go use the bandwidth to watch Paramount Plus. When I'm not using bandwidth for that, I use it to go watch, we'll say, Disney. So I can basically have almost unlimited feeds of content coming in because I'm not using all of them at the same time. Got one TV, there's only so many things I'm going to watch at once. But I'm not limited by this fixed relationship of the one-to-one. Channel 2 is KCET, or Channel 3 is KCT, Channel 2 is KCBS, Channel 7 is ABC. I'm not fixed to that relationship. My streaming, that data that I'm paying for, I can use it to watch whatever I want, whenever I want. Almost unlimited. That's the same concept of what smart routing is. Go get the content you want when you want it, and when you don't want any more, get rid of it and put something else in its place. So that's the idea that we have, all based on the benefits and the many, many wonders of 2110. So I think I'm nearly out of time here. That's the basis for my presentation, hopefully simplifying the idea, contrast, if you will, to the great information that was presented earlier and all the wonderful presentations. The idea, if you're thinking about 2110, if you're not sure, again, there's lots of people without full network engineers on staff that have put together beautiful, elegant, simple systems, and they're taking advantage of all the great benefits of 2110, even though they have one person on staff that is their only engineer, that sort of thing, who doesn't happen to have a degree in networking and that sort of stuff. So lots of great things for 2110. It's available to everybody. The cost of the products has come down thanks to a lot of the great manufacturers in this room. It's really one of the great things about the future that we can look forward to is you can basically get into it now or look forward to an even bigger, brighter future with 2110 as we go down the road. If you've got questions about that, hopefully here and abroad in the streaming world, you can take a little QR code there and take a look at some of the products that Panasonic makes, not the least of which are the cameras that we're using today to stream this, and Keras Switcher and a whole bunch of other cool stuff. So Now, I guess is the time for questions. Please.
As a analogy to the SDI world, couldn't you just have in front of your switcher an SDI router which does the same thing? And going back to your 2110, what if you want to have a preview of the other camera? Just those two questions.
So, great questions about, I'm presuming, the concept of smart routing that we were talking about before. So, it's been around for quite some time, since SDI and even composite analog switchers have existed, that a router would do a subfeed using tie lines quite often into the switcher. And all you as the TD had to do, besides switching your big show, which might be the super whatever, is then go to another little switcher known as your router and do something there. Now, ask me as a TD, is that fun for me to do? No. The worst thing I want to do is take my eyes off of my control panel, which I am paid to touch every single second of every day, and go to some other device to then reroute signals into those open spots, just as I'm going back and being cursed at because I missed a cut that they asked me for. So, could you absolutely do that? Is that something that's done part and parcel? Absolutely. Is it not great? Absolutely. Because it is tough to manage two independent machines at the same time. Now, there's some ways you can build in macros and things like that to send it off. The idea here is, I don't want to do any of that. I, as a TD, want to focus on the one thing I'm supposed to do. Just cut my show without any extraneous distractions or whatnot. So I don't have to do that because I'm just pushing camera 1, camera 2, camera 1, 5, 10, 50, 90, whatever, and all of that happens in the background. Not a single thought of mine goes into it. I don't even know that it's happening. I don't even have to program it to do that. It's all done transparently in the background. So it is the idea you're talking about put to the highest level of simplicity and elegance for the TD to do their best work as a TD, not a routing engineer. And, the other suggestion you made or thought was the idea of, actually remind me again the other part. Oh, the preview. So this is again, without getting too far into it, this is a make before break situation. So you're able to preview things by essentially using the same concept. I can put it in preview and I see it up on the screen. I know it's there, it's fine, I have confidence that when I'm about to take it, it's actually going to be there. I'm not doing it essentially as a guest that's going to show up only when I push the button. So I'll see it beforehand.
Would it need a second cable as preview?
No, so not required. The data itself brings it into the system. You see it on the multi-viewer. It's all there, ready to go. So, great questions, by the way. Any other great questions? Oh, boy.
The smart routing stuff looks pretty cool. Are there specific routers it works with, or does it work with specific switches? Like, what method does it actually use to control the upstream devices?
So technically it's not controlling really the upstream per se. It's simply changing the stream ID within the system if you want to think of it that way. I'm drastically oversimplifying it. We can go over more detail in a second here. But yeah, it's not like, oh, it only works with these things. There's some separate data that's telling the switch what to do. No, nothing like that. Think of it more like an NMOS, but backwards.
And I guess that was my question. It's not utilizing NMOS.
But it's actually not utilizing NMOS.
Okay.
It's similar. Yeah. Again, it'll be easier to show you some of the stuff over there. But again, great questions. Please.
I have one more about the signal definition of SMT2110, because back in the old days we had to do key and fill, which even when you wanted to do like just like PowerPoint or any other compositing things, you always had to use a key and fill signal.
Right.
Currently in SMT2110, I only know they kind of try to recreate the approach. Is there any chance to get an RGBA signal as a standard in SMT2110?
Yeah, it's already there.
It's already
in fact, it's already part of KERAS, yeah. Awesome. Yeah, so RGBA or RGB, the video, and the A is the alpha for those who may not have properly heard. So great question, and again, already exists. So yes.
As a standard, or just as a standard in the SMT definition, because before it was more just like a separate key, synchronized key fill stream, right. And I never got really a good answer if alpha was like a really in the standard established stream.
So yes.
Okay.
Yeah.
Is it the same stream?
Yeah. Okay.
Excellent. Thank you so much, Keith. Really appreciate it.
Thank you.
And we do have some time. You're welcome to hang around for a little bit. I didn't want to make anybody seem like they were not welcome. I think if you'd like to learn more about the K-Roasts, the station over there, you're welcome to go into what we call Video Garden. Otherwise, we'll just be hanging around answering questions. And thanks so much for coming.